How's everyone doing?
Apparently they're going to have a new TESS poster out this week for your wall, Daniel.
That'll be fun.
Yeah.
I rely on conferences to decorate my apartment. So as you can see,
it's going to get revealed in the talk after this session. So there's a
perfect
talk with 3 folks from JPL who work within the kind of design and social or outreach department. And so they're giving a talk about how the posters are created in general. And then it's going to be the first reveal of the TESS poster.
Cool. I'll have to pick one up once I'm able.
I know, unlike a normal conference, we can't just go to the table outside the auditorium.
I had at the 2020 AAS conference a truly embarrassing stack of swag that I was taking back to Canada with me.
I know, I always go for stickers and then I like slowly hand them out to students. And then eventually I run out, and usually I use the next conference to replenish myself, but I've been like, I'm totally out at this point.
I like that. That's a great way to.
Everyone loves stickers. Everyone from 9-year-olds to college students loves the Kepler stickers and the TESS stickers, although I had fewer of those.
A lot of the undergrads like putting them on their laptops. Well, everybody likes putting them on their laptops, but the undergrads don't have easy access to them by default.
Yep, exactly.
Jessie Christensen added in the chat that she uses conference swag, stickers, and pins as geocaching prizes. So.
Oh,
that's a neat idea.
That is an interesting idea. Yeah.
By my watch, we have 1 more minute, so we can continue bantering for 1 minute, and then we'll go ahead and get started.
And Leslie, can you remind me of the order? I think I go 3rd before Daniel, right?
That's correct. Yeah. Johanna, Juliette, you, and then Daniel.
Perfect.
My plant's name is Chuck. Get some nice background information here for you.
Okay, well, hi, Chuck. And now I guess it's officially 3:30 p.m. Eastern time. So how about we go ahead and get started? So hello, everyone, and welcome to our panel on exoplanets. And in particular today, we'll be discussing the observations and interpretation of exoplanet mass radius measurements. My name is Leslie Rogers. I'm a faculty member at the University of Chicago, and I'll be serving as the moderator for this session. As a reminder, please go to the Exoplanet channel on Slack to submit questions for the panel. We have 4 amazing panelists joining us today. Joanna Teske is a staff scientist at the Carnegie Earth and Planets Lab. Juliette Becker, who's a 51 Pegasi B postdoctoral fellow at Caltech. Diana Valencia, who's a professor at the University of Toronto, Scarborough. And Daniel Thorngren, who's a Trottier postdoctoral fellow at l'Université de Montréal. Each of our panelists have pre-recorded an extended 20 to 30-minute talk, and they're all available on the conference YouTube channel. So if you haven't already, I strongly encourage you to check out those talks. To begin our session today, each of our panelists will present a short 3 to 5 minute summary of the key points of their extended talks. And after these summaries, we'll open up the panel to more of a discussion and take questions from the audience. So first up, we have Johanna Teske from Carnegie EPL, who will tell us about measuring planet masses with extreme precision radial velocities.
Look good? Thumbs up? Okay, yeah. So hi, everyone. Thanks for joining in on our panel. I'm just going to go over kind of the key takeaways from my pre-recorded talk. The first one was that precision RVs have been and will remain an important tool for characterizing exoplanets complementary to transit observations. I think everyone can get on board with this. you can see in these little plots that I made how RV planets are enabling us to, or RVs are enabling us to detect longer period planets and potentially those on more temperate, cooler orbits. I talked a little bit about how mass is an important fundamental parameter, and a little bit about bulk densities, but that was the topic of Deanna's talk more. And then I mentioned how from Kepler, we really know that small planets are common, at least at short orbital periods, but transit probabilities can be low. And so in a limited sample of stars in the solar neighborhood that we might be able to detect and characterize habitable planets around, we want to be able to find those even if they don't transit. And so RVs are a way to help us do that. The next takeaway was that there are a lot of hurdles remaining to detecting Earth analogs with RVs. I think a lot of the growth in the field has come through advances in technology along with analysis methods to find those temperate terrestrial kind of Earth analog planets. But as you can see from this observation here at the bottom of the sun as a star from Harp's north, those are the gray points. And this green line is the Earth signal. And so we're just kind of far away from where we need to be to make these types of detections. And I think one of, if not the biggest hurdle, is that the stellar variability. Stars not being constant, well-behaved sources of light, they have, granulation and spots and different magnetic phenomena. And so this will be, I think, a big focus of research in EPRV moving forward. And there are also these, I'm sure there are more hurdles, but the other ones I talked about were instrumental errors or things that instruments can induce in RVs, just getting enough cadence and time to be able to make these observations. Oh, and then Earth's atmosphere. The next takeaway was that we're not letting those hurdles get in our way, or at least not letting them stop us. And now I think is this really heightened development of new PRV instruments that are pushing our technical capabilities in the optical and the near infrared. So, we've reached a little bit of a plateau, but hopefully in the next 5 to 10 years, we'll be moving more in this direction. And on this slide, I'm just showing a plot from the ESPRESSO spectrograph and one from MAROON-X, where precision below a 0.5 meter per second has already been demonstrated. So this is really exciting. See these instruments coming online and starting to produce results. And then I finished the talk just talking about some synergies between PRV and TESS and how they're sort of complementary and enhancing the scientific impact of each other. So I talked about how RVs help to detect TESS single transits or to confirm them. So this was a cool example of TOI 1456, where it was thought to be just a single transiting planet, but actually getting the RVs pointed towards a transit that had been missed in the light curve before. This is an example of another TOI 186 that had a rotation period in the star very close to the planet period, but having the TESS data enabled us to try to make sure that the stellar rotation signal was not influencing the measurement of the planet's semi-amplitude and thus mass. So far, I don't know that there are any TESS planets that have atmospheric detections. I looked into this, but they're going to produce they're producing good atmospheric targets, including using high resolution spectroscopy from the ground. And then something I'm really excited about is TESS's contribution to planets around young stars. That really started with K2, but TESS is adding on to that. And so that enables us to study, planets over a range of ages and look at planet formation and evolution through time. So with that, I'll stop and I guess take questions in the discussion. I look forward to hearing from the other panelists.
Great, thanks, Johanna. So next we have Juliette Becker, who will be telling us about measuring planet masses with transit timing variations.
All right, excellent. So I would like to point out a few of the ways that transit timing variations can help you find masses and actually other properties about the system as well, and also some of the difficulties with using this method. So I'm going to start with what can cause transit timing variations. And there's two main causes. So transit timing variations can be caused by star-planet interactions. And these effects generally cause a transit to drift forward in time or regress backwards in time. But I'm not going to talk about those today, because what we really care about with transit timing variations most strongly is characterizing planets. And planet-planet interactions can cause very strong, large amplitude transit timing variations that you can use to actually quantify the masses and other orbital parameters of the planets. So here is a real schematic animation I made that shows what are you actually looking for when you say a transit timing variation. So the gray model in the middle panel is a Keplerian model, where you'd expect if there were no perturbations in a system, a transit will reoccur at precisely the same orbital period repeatedly. Then in blue, I showed a planet experiencing transit timing variation, so it occurred slightly early or slightly late. And the curve on the bottom, which is the observed minus calculated time of transit, this is what people are referring to when they talk about a transit timing variation curve. It's basically the measure of how early or late a planet transits compared to what you'd expect if it were on a purely Keplerian orbit. So this is what the data looks like. This is how you get TTVs from a light curve. Next question is, what can you actually do with those? So here is an example model of one particular really large TTV amplitude system, KOI 142b. So we'll call this panel the correct solution. But now I want to show you guys what happens if you change just one parameter in the system's configuration. So this system has two planets, but we're looking at the TTVs that the inner planet shows. So let's say that we change the period ratio of the two planets. I'm looping through period ratios here. You can see the number on the bottom. And what you'll notice is whenever the period ratio comes close to a commensurability, so close to a mean motion resonance between the two planets, which you see at like 1.8 and then again at 2, you get really large amplitude TTVs, much larger than what we saw in the true data. So period ratios the transit timing variations depend very sensitively on the period ratios of the planets. Additionally, if you change the angular alignment of the two planets' line of nodes, then you will also get some slight variations in the transit timing variation amplitudes. And that's just because the orbits line up differently. It affects how the conjunctions line up compared to each other. Next up, if you compare the if you change the eccentricity of only the inner planet, then larger eccentricities mean larger TTV signals. There's also some degeneracy with eccentricity and omega, but that's too much for 5 minutes, so I'm not going to talk about that. Finally, if you change the mass of the perturbing companion, again, the amplitude of the TTVs on the inner planet that you're looking at are going to get much larger. So hopefully you've looked at all these animations and you're thinking, okay, that's a whole bunch of different effects that can cause the same thing, which is measurable transit timing variations. And this is actually something that we have known since Kepler 19 in 2011. So this is a plot showing all the potential orbits of the companion in this system based on the TTVs of the inner guy. And there's a whole bunch of options. So this is the danger of TTVs. There's a lot of degeneracy between mass of a companion, eccentricity of the planet you're looking at, and all of those other parameters. So here's a recent example from TESS that kind of shows this. So this is TOI 216, which is a really great system that's been characterized by a couple different groups. The corner plot that you see on this slide is kind of the characteristic result of a TTV fit. You're trying to get constraints in the posteriors of all the different orbital parameters. And you'll see here that there's a lot of cases where you have lots of not only degeneracy between parameters, but also potentially bimodal distributions. And this is because of those animations I just showed you, that sometimes different parameters can kind of mimic each other and both cause TTVs. So what do you do about this? There's a few different solutions to this problem. I'm going to skip over the challenges for now, but the TESS solutions are you're reobserving old systems, which extend your baselines, and then you're also getting brighter targets, which allows you to do radial velocity follow-up. So I want to end back on TI 216. This is another paper that was done on the system, where a bunch of transit data from multiple sources was combined with radial velocity data to get a much better constraint on the orbital state of the system. And so by combining these types of data, you can not only get masses from TTVs, but you can break that degeneracy and actually learn more about the entire state of the system, including the eccentricities, the angular alignments, and the exact period ratios. And that is the strengths and weaknesses of TTVs.
Awesome. Thanks so much, Juliette. Next up, we have Diana Valencia, who will tell us about the interpretation of small planet mass and radius measurements.
Okay, can everyone see? Good, okay. So trying to summarize the key points, I'll first say that my goal is to convince everybody that the composition of rocky exoplanets can be used to constrain planet formation theories. And that's because here I'm showing you a figure of radius versus mass of the planets for which we have good data. These planets lie in what we call the rocky region, and therefore to understand their composition, giving them a radius and a mass, the most important factor is to determine the amount of mantle versus the amount of core, or the amount of magnesium, silicon, oxygen material versus the amount of iron heavy material. And so really it's a better constraint problem. It's not exactly a one-to-one because there's other degeneracies, but I won't talk about it today. You can ask me in the questions. And so what we did with my student a year ago, Michael Plotnikov, was to look at this sample and see what is the data telling us about the variation in composition of planets and how does it compare to stars. And so we revamped our internal structure code, we combined it with an MCMC and obtained the composition of all of these planets that I'm showing you here and compare it to the stars. So just to recap, this is the line of the mass radius line of a pure rocky composition. We call it the rocky threshold radius because any planet above that cannot be rocky. Any planet below it could. And then you have lines of compositions, constant compositions with increasing amount of iron. And so what happens with composition is that these planets, even though they could be rocky, it's also true that they could have a volatile envelope and more denser material. And so what we did is divide the planets that could be volatile and are closer to this line versus the ones that are more embedded in the region and more compact. And so those are the ones that are green over here versus the purple over here. So this is our main result figure, where you have iron to silicate ratios and iron to magnesium ratios of the planets with the error bars. And so these are the ones that are embedded in the region, and these are the ones that could be volatile, meaning that these ones could really move if they have a volatile envelope towards this side. So these are really lower limits. And we can compare them to the refractory ratios of stars, which are the ones in red, to show that it really seems, despite the large error bars, that the planets span a larger composition. But this, we also showed it in a different space. So this is the comparison between the stars and the planets. And you can see that there's an excess of iron-rich planets compared to stars. But we also showed a comparison in core mass fraction space, because this one is a linear comparison, whereas this one is non-linear. And you can clearly see here that there's some excess. I wouldn't pay too much attention to this region again, because planets that are low in iron could just be have volatiles. And so we can now translate the composition of stars into what core mass fraction would they, if the planets that they were born with had the same refractory ratios, what kind of core mass fractions would they have? And so showing primordial composition is here in purple. And so that way you can visualize clearly that the planets span a wider range. And these planets over here, which are color-coded with respect to temperature, pose a challenge. You'll see in a second why. This is another way of projecting this discrepancy. And there were other works that followed. And I believe you heard about, sorry about the pronunciation, Adibekyan, earlier this morning. And so I consider this to be the first step into using this as a tool to understand planet formation. And for anybody that wants to be able to plot figures like this, you can go to Michael's GitHub account to get the data. And then a few other takeaway points is that I would like the astronomy community to move away from using bulk density, because bulk density confounds composition and pressure regime. You can see in this figure that Mercury and Earth actually have the same bulk composition, but they're not chemically the same. And so what we use is the uncompressed density, which is what you see over here. And it's a different space that you might not be familiar with. And in this space, we have uncompressed density as a function of radius. So we basically took all the composition of the planet and move it to a reference pressure, and therefore only as reference pressure, we take away pressure, we're only comparing composition. And for this particular space, for a given radius, we are biases towards larger uncompressed densities. So the fact that we are biases to detecting things up here means that perhaps there is some sort of envelope, some threshold above which planet formation cannot enrich planets more with iron. So it seems like maybe the maximum iron enrichment is around 6 grams per cc. But again, these are big, large error bars. I think we're just at the beginning and we should monitor these values. And then if you just look at the planets, so these are planets that are color-coded with respect to their irradiation levels. And if you just look at the ones that are big symbols, they're the ones that are very highly irradiated, that if you believe that atmospheric evaporation has sculpted the super Earths, they should be bare. You see that these planets have a wide range in their composition, iron-poor, iron-rich planets. And intriguingly, let me just see. Okay, intriguingly, if you order them as a function of insolation, again, we don't see a big trend between the core mass fraction and the insolation, but we do see planets here that they're either very iron poor and we don't have a way of forming them, or they're very highly, or because they're highly radiated, but have a volatile envelope, somehow they manage to escape losing this envelope. And so again, there's only 3. We don't need to lose any sleep, but something to keep in mind. And do I still have a minute, Leslie, or am I done?
I'm afraid your time is up. Sorry.
Okay. Just to say, I was just going to say that we have models that show that forming very iron poor planets or very iron rich planets is not possible via giant impact collisions. And with that, thank you very much.
Yeah, thanks so much, Diana. And everyone, please go see Diana's extended talk as well for like the slides we had to skim over. And so now the anchor of our planet mass radius measurement relay is Daniel Thorngren from the University of Montreal. We'll be talking about the interpretation of giant planet mass and radius measurement.
I'm going to have a great time in the relay because I sort of didn't read the instructions very carefully and did a 1-slide summary. So I'm doing similar, I'm interested in similar things to Diana, but I am pretty thoroughly focused on giant planets because they're easier. And so as far as that goes, we have the data on the top half of the slide for planets that have both masses and radii, in addition to the other stuff that's easier to get, like period and semi-major axis. And that's sort of the bread and butter of doing interior structure modeling or trying to figure out what planets are made of. You kind of need both. And we have a pretty good number of them. Most of them are hot Jupiters because those are the easiest for both RV and transit. But we also have a lot of pretty valuable cool giant planets. Cool. These are just less than 1,000 Kelvin equilibrium temperature. And they're important because they don't seem to exhibit any hot Jupiter heating effect. And so what we can do with these well-characterized planets is do structural evolution models where you're basically just taking these inputs of the mass, the illumination onto it, the insolation, whatever you want to call it, some presumed composition and the age, and you get out a radius and an intrinsic temperature. So here's some evolution tracks of the radius against age, plotted for different heavy element masses. And you can make a similar plot for intrinsic temperature, and I have it in the slides. And But of course, we don't really know. We can measure the radius, but we don't know the composition. So the real interesting thing to do is to work backwards and do a retrieval on the composition given the radius. And there's definitely modeling assumptions that go into that. So it's not as though we're going to get an exact composition onto these planets, but you can get a rough idea of what's going on with their interior compositions. And so I've got an example retrieval here for a planet that I can't remember. Now, as far as TESS goes, TESS is great for this kind of work because we're going to find a lot of planets that we can follow up with RV. And because they're often going to be around bright stars, we might be able to find planets that are readily characterizable. So for example, we might be able to get atmospheric abundances for some of these guys relatively easily. And that's particularly exciting for me because if we have an atmospheric abundance, we can say, well, that's probably similar, modulo some kind of rainout or chemistry or whatnot. You got to think about it a little bit, similar to the envelope metallicity. And then the bulk metallicity, you can compare those two and figure out like, well, does this planet have a core? Are there metals in the bulk that are missing from the atmosphere? And so that's really interesting to me. But I also would like more cool giant planets, because they're a really great baseline for studying these things. And also if people can manage it, super Jupiters, more than a few Jupiter masses are pretty rare, especially if they're relatively cool. But if you find any, I love them, and please be sure to publish them because they're very exciting to me. So that's all I got. Thanks.
Great. Thanks so much, Daniel. And thank you to all our panelists for their kind of summary talks. So we already have a number of questions from the Slack channel, and I think I'd like to start off with a question from Ethan Cruz, who that kind of touches upon the topics presented by all four panelists. So Ethan asks, as someone who hasn't followed the field super closely, is there still tension between TTV and RV mass measurements, or has that been resolved? Relatedly, I think there were concerns that RV mass measurements were biased towards more massive values for various reasons. Is that still a concern, or has that also been addressed by the field? So maybe we can start with Johanna and then Juliette to talk about kind of biases at the observational level, and then ask Diana and Daniel about the interpretation.
Yeah, so I'll actually, Julia and I were chatting, and I'll let her take the TTV question. But the idea that PRV or RV derived masses were biased towards more massive values, that is still an issue. And Ben Monte has a really quick paper that just illustrates this in a simulated example, I think from 2018. And so it has to do with, there's an aspect of it that's which targets we're selecting to observe, but then also how we're conducting the observations. And that the way, we're scientists, we like high confidence, high sigma results. And so that can introduce bias in basically the K value, the RV semi-amplitude that you're settling on for your planet. So I would say that is not really a resolved issue. I think it's something that people are paying more attention to. But it's something that, especially as we get to the smaller and smaller planets where the K values are smaller and smaller, it's something that we're going to have to be careful about.
And then as for the discrepancy between RV and TTV masses, the papers to look at if you're interested in this are Jason Steffen's 2016 and then Sean Mills, Matz's 2017 paper. The really cool result that Mills found in 2017 is that the discrepancy does not exist for planets with periods less than 11 days. You only start to get the discrepancy between RV and TTV masses beyond 11 days. And a reminder, this is really a population level discrepancy. There's not too many individual systems that have statistically discrepant masses. Some of the examples that people used early on have been since figured out to be just due to differing priors on the fits, for example, usually on the TTV side. But if you're looking at population of TTV planets in general and RV planets in general, so the discrepancy really only exists outside of 11 days. And there is a bunch of observationally bias related reasons why you'd have this discrepancy. So as an example, the RV population tends to have a higher period ratio between adjacent planets than the TTV method does. As I kind of pointed out in my slide, I had that animation that showed how the TTV signal scales very sensitively with the exact orbital period ratio and other parameters. So the TTV method is really probing a different population of planets than the RV method is. So I would say I'm not 100% certain, because you can never be 100% certain with anything, but the discrepancy between RV and TTV masses is probably driven by observational biases and the differences in the two planet populations that are probed by those two methods. That's a great question, though. It's an interesting topic.
Diana, would you like to add any thoughts on kind of the implications for kind of the theoretical interpretation of the population?
Yeah, thank you. Because for the small planets, actually, mass measurements are what are keeping us from making definite conclusions. It really is our bottleneck at the moment. And for example, the sample that I showed you is a very heterogeneous sample. And because there's, as Johanna pointed out, work by Montet, that there's a bias towards larger masses. In a way, we're biased towards getting iron-rich planets. So we do see that excess, which we still have to explain, but perhaps they're very like outliers compared to if we would look at the planets in a very homogeneous way. So those the way that it's being observed translate very much directly into what we observe. And that's why I like to say that this is preliminary. We're building the database not to make definite conclusions, because we need to work with this. And then as we move forward, I love that we're talking about these biases, because the only way that we're going to correct them is that we talk about them and see as a community, what can we do together to make them go away as much as possible. And so I would like to propose that it is for observers, and correct me if I'm wrong, one of the things you have is a goal on accuracy. Let me get a certain accuracy in the mass. If we can move away from a percentage accuracy to an absolute accuracy, that might help some of the issue here with biases.
Daniel, I realize the giant planets you study are a bit easier to detect, but did you want to add anything about biases and how they affect your population level studies?
Yeah, I mean, so fortunately, as you say, giant planets are easier, so we don't have to worry about this as much. And oftentimes for retrieving composition, even uncertainties up to like 20% in mass are often enough, just because the mass, once you get out into the Jupiter regime, is sort of not very important for determining the radius. It can matter somewhat more for hot Jupiters, but then those are the ones that we have tons of, and RVs are easier. So it's less of a concern, but nevertheless, if you're very worried about it, certainly if you can figure out what the observational biases are, there's no reason that you can't incorporate that into a Bayesian population model. I mean, that is something that the Bayesian statisticians have studied extensively. So.
Great, thanks. So next, I'd like to move on to a question that comes from Sam Quinn. And so he asks, so PRV teams will measure the masses of the low-hanging fruit, brightest stars with largest semi-amplitudes, without any prodding from theorists. If you could persuade teams to focus on more challenging mass measurements, is there a region of parameter space that would be most useful for constraining small planet formation? And so this was perhaps first for Diana, you said, but for any panelists. So maybe let me hand that off to Diana first.
Yeah, thank you for that question. So I think there's two routes of going about this. If there's a population study, then I think you should not talk to theorists and just look at a very unbiased metric and then go with it, which is what Johanna did with her MTS survey. But if you're looking at, let me try to address a specific question, a specific physical question, then I think you do need to talk to theorists and look for these very weird planets. So there are some that are incredibly iron rich. And but one of the things I found is that if you have more than one measurement of a planet, even though they have in the vicinity, they agree with masses and radius, it still moves around, and it has such a big impact on what it means in composition that I think it is very much worth looking at those outliers and going and observing them a lot, as well as the very iron poor planets. And I'm happy to give you the names of the ones that are very highly irradiated and very iron poor, because again, I would love to find out if they have an atmosphere indeed, and if not, are we sure about that mass? Is it really maybe it's a volatile planet, and then we have, I don't know, but it's another worry. But in any case, we need to know. So that's that. I would say that those are the two strategies.
Daniel, do you have any kind of wish lists for observers?
Yeah, I mean, so as Diana says, if you're trying to do any kind of abundance calculations for how common planets are, asking the theorists what to look for completely ruins that. So don't do that if that's your goal. But if you're just trying to understand, well, how does this category of planet works, like cool Jupiters, then that's okay. As long as the people doing abundance stuff know that you were searching for something in particular when you look that up, or when you followed that up, rather. Yeah, I sort of mentioned this in my slide. I like cool giant planets because they're not just useful for themselves, but they also set a nice control group for hot giant planets. I like super Jupiters. We don't have enough of them. So obviously you get double points for cool super Jupiters. And anything that makes the atmosphere people excited, I'm excited about too. I guess is my sort of, I mean, the tricky thing about the super Jupiters is often you have a transit radius and you're like, oh, well, it's about a Jupiter radius because of course it is. That doesn't tell me much about, like there's going to be some variation, and that variation is interesting, but you can't tell in advance that you're looking at a super Jupiter until you try doing RV. But on the upside, once you start doing RV, you know more or less immediately that it's really high mass. So.
Juliette, how about from kind of a system or dynamics approach, kind of with TTVs talking about multi-planet systems? So from that perspective, what would be your kind of wish list?
Yeah, so my favorite thing that you can do with TTVs is get in addition to the masses of the planets, which is obviously super imperative, but you can get the complete orbital state of the system, including the eccentricities and the relative alignment of the arguments of periastron. And those kind of constraints allow you to make better inferences about planet formation, because different mechanisms of planet migration will lead to different orientations of the planet's orbits with respect to each other. And to do that, you kind of need a lot of really precise data for individual systems. So in my mind, I love it when people really dial down on the really interesting systems and continue to observe them, so you can get really great constraints on these parameters. Although broader population surveys are obviously useful as well, but those really high precision solutions are kind of my favorites, because those give us great systems you can get dynamical constraints from.
And Johanna, this question was kind of phrased in a way to aim at theorists, but I'd be really curious to get your perspective as an observer. Like, what is your wish list that you would love the theorists to do that would help plan observations?
Yeah, it's interesting that like everyone is saying we want to study individual planets and drill down on them, and that's not what I've been doing, but that's useful to know. So the thing I've been interested in most recently isn't exactly for theorists, although I'm sure like it would be informed by that, but is more experimental. I'm really interested in trying to understand the interior compositions of exoplanets by observing their atmospheres. Okay, so what happened? How do we get what's inside the planet out of it? What are the different things that can outgas? Does that produce an observable signature? And I think a lot of the high pressure temperature experiments that have happened in the past were pretty Earth focused. I know that's changing. There are several people in labs across the country who are working on this. But as we move into this era where we're starting to make the smaller planet observations, it would be great if I had, and there are some, but even more, predictions for, if I see this, it means this, for something about the interior of the planet.
Juliette? Sorry.
No,
Juliette first, and then we'll come to you, Diana.
Yeah, so I was going to say, actually, I completely agree with you, because some of the predictions from dynamics that we're really trying to move towards is getting constraints on interior structure. But as a dynamicist, the constraints you get on interior structure are the power index of your density profile, not anything chemically useful. So I think combining those dynamical constraints on interior structure with the much more precise, hopefully someday chemistry, that would be really interesting.
Yeah.
Diana, sorry, go ahead.
Yeah, so I shake my head because I would love to give you guys, if you find this, it means this, and if you find this, it means that. And at least for the small planets, that will most likely not be the case. Maybe for certain things it will, but most likely will not be the case. And in fact, I would like to argue that we try to move away from that goal, because I suppose, especially for observations, and as I was looking at proposal for JWST and thinking, it is wonderful to say that you have a smoking gun of a detection, but for the small planets, that's not going to be the case. And if we look for that, then we're not going to observe them. So I think we're going to have to deal with the probability. We will have to deal with that uncertainty, and that's okay. I think that that's still worth pursuing, because in that process, we will, I'm sure, discover many things, and we'll rule out something else. So more than thinking it will certainly mean this, I think it's more realistic to say it will probably not mean that. And I know it is not as clean, but I think that's what happens with in planetary scientists, or scientists know it. It's not as clean. It's very messy, and in a way, it makes it very interesting, hopefully, to people.
So kind of building upon this topic, I'd like to bring in a question from Melissa Hobson, which was directed towards Daniel, but I think it somewhat applies to all the modeling that's being applied to these planets. So she asked, regarding the assumptions in the models, could you recap what they are and which you think are most or least robust? So maybe that could be a whole kind of hour-long topic in itself, but maybe if you can each kind of describe the kind of least robust, weakest link in kind of the modeling assumptions.
Sure, I'll start. That's all right. So, I mean, the first thing that springs to mind is the uncertainty in the equations of state we use for our models. But the thing is, that's actually more important for solar system giant planets and possibly lower mass planets than giant planets. Although with giant planets, you have the problem that hydrogen is kind of hard to model at super high pressures compared to things like rock, which is relatively easy. But it still ends up not being as important as which metal you're using. So, are the cores of giant planets rock? Or are they rock and water? Are there, I mean, it doesn't really matter if you're using water or methane. They're too similar once you get to gigabar pressures for anyone to really care, but megabar pressures. Gigabar would be like brown dwarfs. The iron still matters a little bit, but it's not a huge deal. So that ends up being more important than the equation of state stuff. But more important than that, I'm working my way up here, is did anything weird astrophysically happen to the planet? Because it's really hard to tell sometimes, and you can end up in weird states. So if you had a recent giant impact or something, or if if the planet is currently tidally circularizing, and at the very least you can always tell, oh well, this, if you do enough observations, you can work out, oh, well, it's not on a circular orbit, but it can be a little bit trickier to figure out what the tidal Q is. And so how fast is it circularizing? Because if it's circularizing fast, that energy goes into the planet and that makes it hot and that makes it big, but it's sometimes hard to tell whether that's happening.
Maybe Diana, can you chime in and talk about kind of the weakest link assumptions for smaller planet modeling?
Oh, so So our models are pretty good. I mean, we do not have equations of state at high pressure for the cores, and at some point it'll become a problem. It's not a problem because it doesn't change. We think we have a good theory and won't change very much what we assume. But as the precisions get better and as we get more planets, that will start mattering. So in our case, I would say it's in our assumptions. So no, we have pretty good, I mean, how can I say this? We know what we need to put in that we won't be able to, that we won't be able to, how do you say it, constrain. So for example, if the planet is segregated into a core and a mantle versus a planet that didn't completely differentiate, we won't be able to know. I mean, at least not with masses and radius only. And so we just put that as a one or the other and see. So we know we have a pretty good understanding of what assumptions go into the model. And the only thing that is stopping us from making definite conclusions is actually the observations. I would say that, as I said before, and I want to make a call to everybody that's looking at masses. Thank you. Your work usually does not get as, it's not very glamorous because you need to, look at these planets that are small planets for so long. And then after years, you get one paper, whereas before you get a nature paper for every Jupiter-like planet and with a lot less work. But it is super important. It is super important. So just a shout out to everyone who's doing that work. Really, we need it. And thank you for providing that.
Yeah, thanks so much, Johanna. So Juliette and Johanna, do you want to add anything about kind of weak link assumptions in TTV or PRV modeling?
Yeah, so I have a weak link. I don't even know how to describe it. It's not really a weak link, but in TTVs, there's no like uniform process of going from data to orbital solution. Everyone uses a different code. Some people use n-body, some people use analytic approximation, some people use a mix of both. Everyone uses different priors. Everyone uses different criterion for, we're going to use an eccentricity of 0 in this fit. We're going to let it float in this fit. We're going to fit e cosine omega in this fit. We're going to fit them separately. I'm going to cut myself off there before the music plays. But since everyone's using different fits to get the final results, there's a whole bunch of systematic biases that are being incorporated differently into every solution. And so, that's a huge issue if you're trying to do a population comparison of all of those different results.
And Johanna, what about in terms of interpreting PRVs? I know you talked about a lot about kind of stellar activity and how to distinguish that. What's kind of a limiting factor there?
Yeah, well, I was going to actually address another question that was in Slack, which was a limiting factor is we don't know if there are other planets. And I mean, that's true for transiting systems as well. You don't know if there are non-transiting planets or outer planets, but I think especially when we're getting into smaller signals, that's a limiting factor with RVs. In terms of stellar variability, this is a pretty active area of research trying to understand exactly how different stellar phenomena influence RVs on what timescales, and how to separate out those signals. There's been some work done on, for instance, looking at the wavelength dependence of radial velocity observations, because stellar activity is different across wavelengths, whereas planets should not be. And so I think that's really promising, but that, like I said in my talk, I think that is probably the biggest hurdle for getting down to smaller and smaller mass detections. There's just a lot of unknowns. And so that, I'm just ticking them off. For studying sun as a star, I think that's really helpful because that gives us the spatially resolved information. We sort of know what the answer should be in terms of what is happening on the star, and we can look directly at how that is influencing the RV measurements. Yes, our sun is not, indicative of every other star, but that's sort of where we have to set our benchmark for right now.
Great, thanks. And so I'd like, since we're approaching the end of our time, I'd like to take the moderator's prerogative to ask the last question. And I was wondering if I could ask you each to whether you have any predictions for what you expect to be the most exciting developments in your specific area of research in the coming 5 years. So if we did this panel again at the TESS Science Conference 4 or 5, do you expect your talk or this panel discussion to be different? So maybe I can hand that off to Juliette first.
Yeah, so I think we've kind of only scraped the surface of the potential of the test targets for TTVs because they're so bright compared to the Kepler systems that were analogously interesting. So the Kepler systems were often great TTV systems, but you couldn't follow them up from the ground, definitely not with photometry, often not with RVs. With TESS, that's no longer the case. Like TOI 216 is a great example of you can combine the TESS data with data from ground-based observatories, you can get RVs, you can put them all together. So I think hopefully for TTVs, the way forward will be actually to combine TTVs and RVs together and have more systems where you have both components of the data and you can do a uniform fit and kind of smear over the degeneracies in both methods by supplementing with the other. So I hope that's what I hope to see in the next 5 to 10 years is a whole bunch of papers that do really great in-depth analysis on systems using data from many data sources.
Daniel, would you like to go next?
Sure. I suppose for my stuff, if we could, the dream here is that TESS will find a few really easy to characterize giant planets that we can do good, strong atmospheric follow-up on with James Webb when that launches. And then we'll be coming back here and saying, well, now we have several planets that are better characterized than anything we've done before. And I mean, that will be exciting for many other reasons in addition to interior structure stuff. But for my part, I'll be thinking about, well, if we now have what the atmosphere is made of, what can that tell us about the internal structure? That is like, that might constrain the envelope, which means that we can sort of estimate the core mass roughly. I think that'll be super interesting.
Johanna?
So of course, getting down to smaller masses, smaller planets, but actually a question that I'm really interested in that I think we will have I think we'll have a pretty good handle on by the time for like in 5 years is the influence or the relationship between inner small planets and outer giant planets. That doesn't really necessarily require precision RV, but just long timescale RV observations of systems where we know there's an inner planet. I want to know, are those inner planets, you know, systematically different than the ones that do not have outer giant planet companions?
Yeah, that's a very interesting question. And Diana.
And thank you for letting me go last, because I was thinking about what am I going to say. So I wear 2 hats. So I work on habitability and I work on interior structure information. And I think when it comes to interior structure information, we are going, again, it depends on how well the observations are going to be. But when it comes to this habitability, I think there's going to be a lot of new interesting stuff coming out once James Webb flies. And we have to realize that this small planets, we know nothing. We think we know, we've put in proposals thinking we know, we really know nothing. So I'm very excited to see what the first things comes out, to see how wrong we were in our predictions, or how, you know, did we get something right? And I think if you ask me these questions a year from now, I think I'll have a better way of answering. But in terms of what we can do from the theory's point of view, it involves a lot of bringing a lot of chemical models to understanding how it is that volatiles get outgassed and how volatiles get retained, etc. And combining, I think we're moving towards combining a lot of things. So for example, that was done in TTV. Before it was just the TTV and not with a dynamical analysis, and now they're put together. The same thing is happening with all these fields, that we're putting a lot of tools together, and I think that's going to continue.
Great. Well, we have a lot to look forward to. And so, Alice, thank you for amazing talks and a great job answering all these questions. There are quite a few questions in the Slack channel for each of you that we didn't have the chance to get to in our 50 minutes here. So Juliette, there's a lot of love for your animations and people are wondering like where to find them. So please, I encourage you all to go to the Slack channel and maybe answer the specific questions we didn't get to there. But Yeah, thank you for kind of the first panel of the TESS Science Conference. And so next we have a brief break for 10 minutes, and then the next plenary talk is starting at 20:30 Universal Time, or 4:30 p.m. Eastern Daylight Time. So thanks everyone, and see you at 4:30 for the next plenary.
Thanks,
And
Leslie.
thank you.
That was beautifully moderated.
That was what I
Oh.
was about to say. Thank you for making it go so smoothly.
Oh, my pleasure. That was fun.
Yeah, so is it the same Zoom link for the next session? Is that how it works?
Yeah,
we are staying. We are all staying here.
Yeah. So my guess is everyone can still hear what we're saying right now, though they can't see the chat. Pardon?
That is correct.
That is correct. Yeah, just FYI. Thank you all.
Yeah, no, if there's more questions that we need to answer, I'm happy to just stick around a little more.
Yeah, Diana, Brian Jackson had a question for you in the Slack that I didn't have the chance to do.
Yeah, so with regard to the iron enrichment threshold you described, about 6 grams per cc, does that reflect a planet mass above which there is significant gas envelope accretion? So those planets aren't rocky planets, but are gas-rich planets. Yeah, so if you go see the long talk in that space that I was showing uncompressed density versus radius, what we see is that, so that there seems to be that threshold, but as the planet, as you look at planets that have larger radius, that uncompressed density drops dramatically, actually. And we are biased towards, again, this high regime of high uncompressed densities and high radius, so that regime is real. And so the fact that we don't see that, we think we're seeing the runaway accretion phase. We think we're seeing that by the time they get that size, they cannot do it only by acquiring rocks. But again, the error bars are large, and so we need to keep monitoring, but in a way, it does make sense that there should be some sort of limit at which point the planet just cannot be rocky anymore. Where that limit is, hopefully more data will let us know.
Diana, Leslie, I think it would be better if we use this few minutes we have for letting the speakers of the next part of the session try to connect and check their slides and make sure that everything is working well before we start.
Yeah, sure.
Oh, sounds good. Thanks.
So
yeah, I see many speakers have signed in already, so feel free to go ahead to test connections.
So should I already try to share my screen?
Yeah, I try to share your screen and we will let you know how it looks like on.
All right, okay. Let me.
And I will remind the audience, do not tweet about your talk, I believe.
Yes, that would be great. Thank you. So I think you can see my screen, right?
looks
Yes.
good.
Yeah, that looks good. And that would be the, oh, I think my background doesn't allow me to do the 2-minute whiteboard reminder. I'm going to actually get rid of my Zoom background. Yeah, so this would be the 2-minute reminder.
All right.
Yeah.
Yeah, I hope I can see this, because if I go back to PowerPoint, for some reason that window disappears in the back.
It appears somewhere else on your monitor, Bjorn.
Sorry?
It appears separately somewhere else, the window of the video.
Yeah, I mean,
It happens to me too.
If you prefer an alarm sound, I can also do that. Whichever one you think is more helpful.
Well, let's see. Well, right now you're staying actually where you belong. Okay, so maybe that works. I would also prefer this because it's nice to see, at least even if it's just some images, it's nice to see some faces while I'm talking.
Yep. Yeah, so other speakers, if you want to screen share and test out your connection, feel free to go ahead. I think we still have 3 minutes before going live.
All right, I'll try next. It should be just a sec. Oh, are you okay with me stopping you from screen sharing?
Yeah, sure.
All right. Can y'all see everything look okay?
Yeah, that looks good.
All right.
Yeah, I guess I can also try to share my screen. See if it works out on the video. Can everyone see the video clip I'm showing right now? Or talk?
It's not full screen, but it's showing up certainly.
Yeah, looks okay.
Yes.
Ah, okay. Yeah.
Make sure to click the.
I think this
Not
would be
clearly
full
visible.
screen. Yeah.
Joseph, did you want to try sharing your screen ahead of time? Or are you good?
Yeah, I was going to say I might try screen sharing real quick. Just. Okay, everybody can see the title slide, I hope.
Yep, looks good.
Yeah, it looks good.
That banana slug has gotten much nicer looking since I went to Santa Cruz.
They've had a whole, there's a whole contest over creating a new logo. I kind of like the old one that was from, that was in Pulp Fiction.
Daniel's got it.
Yeah, there you go.
Rodrigo, do you want to share your screen just to test the connection?
Sure.
And after that, Chelsea, if you don't mind, I'm going to make one quick announcement and then you can take off and get the session going.
Yeah, I think we're missing our last speaker.
Oh, okay.
We're missing Tianjun. I sent the email reminder just now.
I will try to
Do that,
catch
right?
him.
Yeah, that looks good.
Okay, great.
Great.
Thank you. You see the full screen there, or?
Right now it's not the full. Yeah, right now it's not in the presenting mode. We can see the side slides.
All right. Okay, I'll put in. Let me see.
So if you want to try to see the actual presenting mode.
Yeah, here it is.
Yeah, now it's good.
Okay, great. Thank you.
No problem.
Okay, I'm going to hop in for one moment and just remind folks that after this next set of fantastic talks, we're going to have a little bit of a break for half an hour from about 6 to 6:30 Eastern time, 3 to 3:30 Pacific. But then we encourage you all to come back to this same Zoom channel because we're going to have a special presentation by 3 of the public outreach and visual strategy specialists from JPL, talking about the design process, the creative process that goes into creating the Exoplanet travel posters and the Galaxy of Horror posters that Daniel and many of us have on the walls of their offices and homes. And we're also going to be treated to a bit of a sneak peek and early display of the new TESS poster that they have been working away on. So that gets released to the world on Friday, but they're going to give us a peek at it and talk a little bit about how it came into being at the end of their talk. And then it'll be time for Q&A after that as well. So please enjoy the half hour off and then hop back on if you want to learn about this great combination of art and science. Okay, and with that, Chelsea, I hand it over to you.
Great, thank you, Jen. So we're really excited to have our 6 speakers to continue our great discussion of exoplanet science done with TESS. And just to remind everyone, please ask all the questions on the Exoplanet Slack channel. And each of the talk will be 12 minutes with 3 minutes Q&A. And we'll start from now. Our first talk is an invited talk from Bjorn Bennick, University of Montreal. He will be telling us about the exciting discovery of LP 791-18. I just want to remind the audience, this talk is actually embargoed results, so it's not going to be recorded. And also, please don't tweet about the result from this particular slide. Nick, can you stop the recording? Planet LHS 3844.
All right, thank you very much. And thank you everyone for being here. I would like also to thank the organizers for the opportunity to tell you all about our work ongoing to measure the mass of the LHS 3844b planet. This is work we've been doing with our colleagues from Chile, especially Nicolas Studio de Fru, and our colleagues from the Grenoble University and from Geneva. I'm Rodrigo Díaz. I'm a professor at the University of San Martin in Buenos Aires, Argentina. So let's start by introducing our planet. This is LHS 3844b, planet detected in 2019 by van der Spek, detected by TESS, of course. It's a very short period planet, 11 hours, around a very nearby Dwarf. The radius has been determined to be around 1.3 Earth radii, and the equilibrium temperature is around 800 Kelvin. On the same paper, van der Spek et al. Used MERTH data to measure the rotational period of the star and determine it to be around 130 days. This is a very convenient object for follow-up studies. So there's been already a couple of works on this with Spitzer and from the ground that determine that the planet does not have a very dense atmosphere. There are also upcoming James Webb observations. So this is a very interesting object to continue characterizing. What we are going to do is trying to get the mass. So the bottom line is that the mass of this object is around 2 Earth masses. So it's solar mass, sorry about that. And the density is around 5 grams per square centimeter. So this puts it around here in the mass radius diagram. So next to the Earth-like composition and pure mantle composition. So this is it in terms of science, but if you stick for another 10 minutes, I'll tell you how we do this and how certain or uncertain we are about these results. So what we did is using ESPRESSO. ESPRESSO, as you know, is the ultra high precision super harps installed at the Very Large Telescope in Chile. And we observed this object for 2 seasons for a total of 25 visits by a program with a program by Studio de Fru. And as you can see, there's been a fiber upgrade between both seasons. So we'll treat this data differently. Of course, there's not too many points, especially that when you look at the ancillary data, you get to see full width hat maximum. In contrast, you see that the rotational period appears clearly in the full width hat maximum. So you have here on the top row, you have periodograms in terms of frequency. And in the bottom row, we have the same thing in terms of period, if you prefer. So you have a signal that is observable in the full width hat maximum, nothing in contrast or signal to noise. And if you extend this to higher frequencies, to the planet frequency, you see there's nothing there, as it should be for real planet. Right, we also have activity indexes that also seem to show something around the rotational period of the star, right? So we have 25 points and activity signal. So what do? We just throw a GP at it? No, because you don't have enough data points, and we can overfit. So why are we going to be worried about overfitting? So let me take a few seconds to remind you about the problem that you can get with small data sets. So here you have data that have been simulated from this real process here, the black line, and we're trying to fit it with different polynomials, right? So this is X, the target, and we fit different polynomials. As you increase the order of the polynomial, of course, the fit gets better, and then after a given point, you start overfit, right? The polynomials start going through all the points, overfitting the data. This, of course, ruins your predictions. If you're going to predict a data point here, you will be very off if you use a very high order polynomial, or if you do it here, anywhere where you don't have any data. But of course, it also ruins your parameter determination, which is what we are interested in, right? We are in the business of inferring parameter from the data. What you can see here is that as you increase the order of the polynomial, the width of the posterior distribution gets wider, gets larger. And if you use a too restricted model, like a slope or a parabola, you will be off from the real value, which is here, marked as a dashed line. Only if you have the right balance between flexibility and capacity or possibility of overfitting, you will get it right? So this is the famous bias variance trade-off. So we have to find the right level of flexibility. We are not going to drop into this. Of course, you may say, we are Bayesians, we don't care about this, or we are covered because we compute marginal likelihoods, but I will show you in a second that this is not really so. And remember that a GP with a square exponential kernel is equivalent to fitting an infinite degree polynomial. So it will go through all the points, right? Okay, so what do? We explore the rest of the data. Here you have all the ancillary observations in a pair plot. You see that they are not very correlated and that they are not easily explainable one from the other, right? So we can define, this means that we can define a linear model using this data. And after some tests, we decide to keep only the full width head maximum. So what we have here is a baseline model with no planet. And you see there's the DC term, an offset between the instruments, and two terms for the full width head maximum, one for each part of the data set. Okay, so we do this, you can see the residuals, the parameters, they are all significant, and the residuals have a dispersion of around 4.5 meters per second. And we explain around 70% of the data variability. So this is not very good, of course, because we haven't added a planet yet, right? When you see the residuals of this baseline model and you plot a periodogram, you see that the rotational period has been quite taken care of. And the largest peak appears at 0.463 days, which is perfectly compatible with the period of the planet. We haven't used any prior on the planet yet, right? So this is a sort of independent detection, only that there's plenty of peaks same height here. But this is the largest one, so this is encouraging. So what we can do here is add two terms for the planet, keeping it sinusoidal, so circular. And when you do this, you find this amplitude for the mass, and you see that all of the terms are significant. We are now to 3 meters per second in terms of residuals, and we are explaining around 90% of the data variability. So the model is much better, as is also confirmed by an ANOVA analysis. We also have a linearized eccentric model, which I don't have time to talk to you about, but this is not really required by the data. So we'll stick with the circular model for now. If you look at the residuals of these simple linear models where there's no GP or anything else, you see that there doesn't seem to be anything there. This is the 10% and 1% false alarm probability levels. Okay, so but can we do better than this? We are not maybe we are not very satisfied with 3 meters per second with ESPRESSO. So can we model the covariance with in the data? Yes, of course, we can do it. So for this, I'll put on my Bayesian hat and discuss how we can construct a GP model with a linear model for the mean function, right? So we'll have two sets of linear parameters, the linear parameters controlling the mean of the GP, and the nonlinear parameters controlling all of the rest, right? Among those parameters, I count the period of the planet, right? Because the period of the planet is something that you have to define in order to get the linear model. And of course, the typical kernel parameters. In this approximation, which is called type 2 maximum likelihood, I will just fix the hyperparameters to their optimized value, right? I'll optimize the likelihood here, and I'll fix, sorry, not this one here, and I'll fix those parameters to this value type, right? Okay, when you do this, if you choose normal priors on W, you get very nice properties. You get analytical posteriors. You get to see here the posterior for the semi-Neptune and the eccentricity in case you were using the eccentric model. And the priors, you get to compensate for the priors, many nice things. You get to analytically compute the marginal likelihood, which is what we did here. And again, even in the presence of correlated noise, quasi-periodic kernels, or combinations of things, the eccentric model is also rejected or less favored by the data. But of course, we want to go even further and take one more step and say, okay, I want to go fully Bayesian, not fixing out, because this is a problem with fixing the hyperparameters. You're optimizing something. You're, again, prone to overfitting, right? So you have to be careful about this. So if you go to a fully Bayesian approach, which you can do, so now the parameters, the hyperparameters are no longer fixed, but they are parameters. They need a prior, which are listed here. And for that, of course, for the period of the planet, we are just taking the period determination from test data. You can sample using ancestral sampling. You can sample the joint posterior distribution using the analytical properties of this object here, which is the posterior distribution of the thank you, Chelsea, of the linear parameters, conditional to the value of the nonlinear parameters. So you can do this. This is the first. I mean, at this step, we run one MCMC for each model, and you get to compare the results. So this is with the blue distribution for the radial velocity semi-amplitude is under the maximum likelihood type 2 maximum likelihood approximation, and this the orange one is with the full model. So here, of course, this might happen because you are marginalizing instead of conditioning, but this might also be a sign of overfitting, even in this context. Of course, you get to see as well the corner plots we all know and love. And what you see here is that for the amplitude, there's one part, this tail here is mostly given by this part of the periodic part of the kernel, which also means that if we use more restricted priors on the hyperparameters, we'll get a better precision. So putting all together, all our models, this plot has a lot of information, but what you see here in the Bionim plots, the distributions of the semi amplitude for the radial velocity, with the mean and error here and the relative error. In red, you have the errors, the remaining errors. So you see that the model works very well when you have the quasi-periodic component, although this might also mean we are overfitting. And in gray, you have the marginal likelihood for all of these models compared to the worst one, which is this one here. That's why it's 0. The ones up to here are analytically computed, and these ones are numerically computed. So when we put all of these together, we can average over all of these models, again, using Bayesian model averaging, and you get a final value, or final distribution actually, for the radial velocity semi-amplitude, which is here. It's quite Gaussian, 6 plus minus 1, and you can turn this into mass using the values from Van der Spek, and see that this is the final result. But of course, in this final, these are still suspect of overfitting. I can tell you why in the questions because I don't have enough time. But even if you're using marginal likelihood to tell which model is more supported by the data, you can still fall into this part. So I will leave you with the conclusions for the scientific part. So it's a mass that's been determined to be 2 Earth masses, 2.1 Earth masses plus minus 0.4. We are compatible with an Earth-like composition, but also to less dense planets, especially less dense planets. This object is now, we knew it already, very good for spectroscopy. and we don't seem to detect any additional signals in the dataset. So the second conclusion and final slide are the conclusions, the summary and the ideas about how we did this, and especially how we should be careful about overfitting and not just throwing GPs at all the systems if we don't have enough data. So that's it. Thank you very much. If you, I've got to answer any questions.
No problem. Thank you very much for the comprehensive explanation of how to fit radial velocity data. I think people really would learn a lot on how to deal with that data.
Sorry.
So just a quick question from me right now. I see the residual of the radial velocity have amplitude of about 1 meter per second after remove the planets. Is that mostly dominated by stellar activity? And could simultaneous ground-based photometry actually help you reduce that error?
Sure. I mean, well, the residuals depend a lot on the model. For the more sophisticated models, we actually have a lower residual, but of course, we may also be overfitting. So, of course, one of the good things about having photometry at the same time, which we did not find, by the way, I didn't have time to explain everything, but we were looking for that, is that you can sort of at least constrain your GP parameters. Most of the variability we are seeing, and probably the capacity to overfit, comes from the fact that you don't have any constraint. The priors are very large, and the priors being very large, then the model can be very flexible. So yes, that would be very good in terms of analysis, especially when you don't have that many points in your series.
And just while we're waiting for Lucia typing in the Slack, I just have one quick follow-up question for you. What do you think the generic lesson is to apply for all the other radial velocity measurements and instruments?
I believe, I mean, when you have a very flexible model, something like a GP regression, what you mostly will have is very wide posteriors, extremely wide posteriors. The mass measurement, the parameter is not biased. This is a good thing about very flexible models. You don't bias the mass, but we may be overestimating our error bars. And this is, as we all know, but we have seen in the panel previously, this is extremely important for modeling, right? I mean, if we get to reduce those error bars, even by a few fraction of by a few percent, this would be a great advantage, especially when you're if you apply this to all the to a population of planets. Of course, I don't mean to say that all of the planet mass determinations are overfit. This is especially a problem when you don't have enough data, when the data are not very numerous, so the data points are not very numerous, right? Otherwise, you should be okay.
Right. I guess I will quickly ask you the question from Lucia. Maria Serrano. Can the multidimensional MCMC with GP be a way of constraining the parameters of the GP, the one that uses the activity indicators? Oh,
the one that you mean, like I guess she means a GP with different inputs. Yeah, yes, of course. But yes, but I'm not very sure we can do this with these few data points. In this case, I didn't show you in detail, but in this case, the hyperparameters of the GP are very unconstrained, extremely unconstrained, right? As you would expect, we don't have enough points. So yes, so but by verifying whether these models are actually overfitting, you can try to find. We can try to find a point in between. These plots meant to show that we are either very good or not good enough. So we are still looking for that model in between with the right level of complexity and flexibility.
Great, thank you very much. And I would encourage you to continue the discussion on Slack.
Thank you all.
Right. And our next speaker is Akanksha Khandelwal from Physical Research Lab of India. She will be telling us in a pre-recorded talk about TOI 1789, an inflated hot Jupiter that she discovered. And so unlike our regular Q&A session, Akanksha will actually take all the questions directly from Slack. And so feel free to type in your question into Slack, and she will be answer you there. I will start share my screen.
Physical Research Laboratory, India. So recently we have detected an inflated hot Jupiter TOI 1789b orbited around a late F-type star. So first of all, I would like to thank all my collaborators that have significantly contributed to this work. And now in this talk, firstly, I will give some brief introduction about TOI 1789, and then I will discuss our observations and analysis related part, and then I will discuss finally our results. So this TOI 1789 is identified by TESS in March 2020 as an exoplanetary candidate, and it has a visual magnitude of 9.7. These are the information that are available on ExoPop web page. And on the right hand side, this is a normalized TESS light curve. So here, these red triangle shows the time of the transit. And this TOI 1789 has a visual binary companion at 1.3 arc-minute separation, and this is observed in long cadence mode. So to further understand the nature of this transiting candidate, we did ground-based observations. So for the photometric observation, we used PRL's 43 centimeter data, 43 centimeters telescope, and acquired several transits. And for spectroscopy or radial velocity measurements, we used Paras spectrograph at PRL and TCS spectrograph at TLS. Now I will discuss these observations in detail. So this is a 43 centimeter telescope at PRL, and it's a plane wave CDK 17 type telescope. And here Endor 2K by 2K CCD is attached, and this is a 3-inch guided telescope with lodestar CCD for the tracking of the star. And for TOI 1789, we used two CCDs for observations. One is TRIAS Pro 814 and another is Endor Icon L 936. So the main specifications of these CCDs are shown here in this table, and we detected 3 transit with the TRIAS CCD and 2 transit with the Endor CCD. So the precision which we achieved with Endor CCD is 0.92 ppt and TRIAS CCD is 1.16 ppt. So the precision achieved with this TRIAS CCD is within 1.3 sigma of the precision achieved with Endor CCD, and which suggests that this type of low-cost interline CCD like TRIAS can be used for precisional differential photometric observation in the near future. So now this is a ground-based light curve that is acquired with the 43 centimeter telescope. So here, this blue data point shows the TRIAS data point, and these green data point shows the Endor data point, and this black one is the best fitted model with the ExoFast V2 software. So now this the light curve acquired from ground-based data are matches with the photometric ephemeris of TESS light curve, which are shown here. Now for the spectroscopic observations, we acquired 16 spectra from Paras and 21 spectra with TCS. So Paras is attached to a 1.2 meter telescope at PRL India, and it has a simultaneous reference mode with optical fiber with the resolving power of 67,000. And for the radial velocity observations, we use the wavelength range of 380 to 690 nanometer wavelength. Now this TCS is attached to a 2 meter Alfred Janus telescope at Nottingham, Germany. Now to determine the stellar parameters, we use the TCS spectra due to its higher signal to noise ratio, and we use the SME package to determine these parameters. These are the stellar parameters that we are getting from this SME package. These are the radial velocity data points from of the both of the spectrograph. One in black one is the Paras data point, and this green one is the TCS data point, and this red curve shows the best fitted model with ExoFast V2, and on the bottom panel we shows the residual. So now to determine the periodicity in the RV data alone, we ran the GLS periodogram and found the most significant period to be 3.21 days, which is similar to the orbital period that we are getting from our photometric observations. And there are another more significant peaks are available in the periodogram, as you can see in this upper panel. At the FFP threshold of 0.1%, and when we remove this 3.21 day signal into this data, these two peaks also vanishes, which suggests that this is an alias of this 3.21 day signal. The residual periodogram are plotted in the bottom panel. So, and for the bisector analysis, we used the Paras data and we checked the correlation between radial velocity and bisector velocity span, and found the correlation coefficient of 0.15 and with the p-value of 0.58, which suggests that the origin of these radial velocity variations are neither due to activity on the surface of the star or nor contamination from the nearby star. So now for global modeling, we used ExoFast V2 software. It is a differential evolution Markov-Chain Monte Carlo modeling code. So for the SED modeling, we used Tycho, EPAS, SDSS, GRI, 2 mass, and all-wise photometric bands in magnitudes. And here this black curve is the best fitted atmospheric model, and these blue circles represent the model fluxes in each pass band, and these horizontal error bars are the bandwidth in each filter, and these vertical error bars shows the measurement uncertainty. And this is the missed evolutionary track. Here this black curve shows the most likely evolutionary track, and this red asterisk shows the model value of age along the track, and this black dot shows the model value corresponding to the T effective and log G. And these are the best fitted transit model. And this slide I have shown in my previous slides, and this is the radial velocity data with its best fitted model. So by the global modeling with ExoFast V2 software, finally we are getting fitted parameter for star TOI 1789. I mean the stellar parameters of this star are shown here in this table. It has a mass of 1.4 solar mass with the radius of 2.1 solar radii with the effective temperature of 5984 Kelvin and with the surface gravity of 3.9 CGS, which makes it a late F-type slightly evolved star, and it has a metallicity of 0.37 dex, which makes it a metal-rich star with the age of 2.8 gigayear, and it is at a distance of 223 parsec with a rotational velocity of 7 km per second. And these are the planetary parameters. It has an orbital period of 3.2 days with a radius of 1.40 and mass of 0.70 and density of 0.31 in CGS, which shows that its radius is evolved as compared to its mass, and it has an inclination angle of 78 degrees and semi-major axis of 0.04 AU, and it has equilibrium temperature of around 1900 Kelvin with the incident flux of 3.14 into 10 to the power 9 per second per centimeter square. Now in this figure, we plot the statistics of all the non-transiting hot Jupiters, and the data are acquired from TESS-Keck database. And here on the x-axis, we plot the orbital separation from their host star in AU, and on the y-axis, we plot the log of G star as an indicator of evolutionary status of their host star. And they are color coded according to their host star's metallicity. So here, the stars with supersolar metallicity are labeled as yellow, and the stars with subsolar metallicity are labeled as blue, and the size of individual dot represent the mass of the planet. Here we mark the TOI 1789 as the red asterisk. And one thing to note here is that the closing planets are more common around the main sequence star. In case of this TOI 1789, it is situated at the boundary, and this boundary can be dictated by the fact and that this type of planets could be engulfed by their host star in course of their evolution in the subgiant and giant phase. And until now, only 8 exoplanets are discovered, including this work around stars similar to or more evolved than TOI 1789, and they are orbiting closer to their host star within 0.05 AU. So here these stars are appeared as diamond symbol. In the next figure, we plot the same statistics of hot Jupiters, and here on the x-axis we plot the planet radius, and on the y-axis we plot the equilibrium temperature, and here the size of individual dot represent the mass of the planet, and we mark the position of TOI 1789 with the red star. And this TOI 1789b's radius is fairly inflated as relative to its mass, and the equilibrium temperature is estimated to be around 1900 Kelvin, and on the total incident flux it received is 3.14 into 10 to the power 9 arc per second per centimeter square. So several studies indicate that the inflation in hot Jupiters would be due to their host stars radiation that they receive, and which indicates that the inflation in this TOI 1789b is due to the high incident flux. So finally, I am summarizing my talk by concluding these points. This TOI 1789 is a slightly bald metal-rich late F-type star, and this TOI 1789 is an inflated hot Jupiter, and derived mass and radius are of the planet are at 4 sigma significance, and the detection of similar types of exoplanets will help us to improve our understanding of the distribution, formation, and migration of hot Jupiters around evolving stars. Now we are acknowledging these people, and finally, thank you for your kind attention.
Great. So since we're not going to have our regular Q&A session, we're going to directly go to the next talk. But I would encourage everyone to continue to discuss the talk with Akanksha on Slack. Okay. Our next speaker would be Joseph Murphy from UC Santa Cruz. He will be telling us about the TESS-Keck survey, and take over from me.
All right. Okay. Can everybody see my title slide? All right. Okay. Yeah. Thank you, Chelsea, for moderating the session, and to the organizers for this opportunity to speak to everyone today. So my name is Joey Murphy. I'm a rising third-year grad student at UC Santa Cruz, where I work with Natalie Battaglia. I also work with the TESS-Keck survey, or TKS, a large multi-institution, multi-semester Doppler survey conducting radial velocity monitoring of exciting test planet candidate hosts using the high-res spectrograph on Keck-1. So today I'd like to talk to you about TKS and how its precise mass measurements will enable the demographic study of sub-Neptune-sized planets amenable to atmospheric characterization. I'll start with a lightning overview of TKS, then introduce the TKS Atmospheres program, and briefly describe our selection function. I'll touch on the progress we're making towards precision mass measurements for those targets, show some preliminary results from our survey in the mass radius plane, and I'll briefly touch on the synergy between our survey and the extended TESS mission and why cycles 3 and 4 are so important to us and to the community. Okay, so like I said, TKS is a multi-semester Doppler survey run by a multi-institutional team. TKS has the goal of measuring the masses and orbits of 100 TESS planets using Keck high-res, as well as the automated planet finder at Lick Observatory. So having access to the 10-meter primary at Keck, as well as at times nightly cadence from the APF, enables us to not only obtain precision velocities, but also disentangle complex multi-planet Doppler signals and keep tabs on long-term velocity trends when we have gaps in night coverage at Keck. We began observing back in 2019B, and observations are ongoing with close to 60 nights on sky at Keck this semester alone. TKS science is organized along 4 axes: planet bulk composition, system dynamics and architectures, exoplanet atmospheres, and evolved systems. To learn more about TKS science as a whole, our target selection methodology, and maybe most interestingly for some people here to see our complete target list, you can read Ashley Chontos's preprint, which is on archive now, and in revision, hopefully for resubmission to AJ soon. You can also hear a bit more about TKS and some of the evolved systems we're monitoring in Ashley's talk tomorrow in session 6, room 1. And just to show a few screenshots of the titles to come to end up in the literature so far from TKS. These are some of the recent TKS publications. You might notice we go straight from TKS 4 all the way to TKS 10. So this is just a hint that there are many papers in prep, in revision, and some even in press. So definitely keep an eye on the archive and ATS for more to come. Okay. So now we're going to zoom in on one of the science themes for TKS, which is the study of exoplanet atmospheres. And just a quick reminder for why we need precise mass measurements of small planets in order to enable atmospheric follow-up in the first place. So this is a figure of 2 simulated JWST transmission spectra, where the planet in orange has an almost Earth-like surface gravity and a relatively high atmospheric metallicity. And then the planet in purple has essentially the same transmission spectrum, but its surface gravity is more than double the planet in orange, and its atmospheric metallicity is much lower. So atmospheric scale height, which is proportional to planet transit depth, is degenerate in atmospheric metallicity and planet surface gravity. Precise knowledge of the surface gravity of the planet is required to break this degeneracy. And so with planet radii in hand from TESS and assuming a precise characterization of the host star, mass measurements are left as the bottleneck for these small planets. And a precise mass measurement is the critical first step in interpreting the transmission spectra and understanding atmospheric composition. But as some of you probably know, the precise mass measurements for these small planets can be quite expensive. So the TKS Atmospheres program is trying to alleviate this bottleneck through Doppler monitoring of 20 systems amenable to atmospheric follow-up. Here I'm showing the 25 TOIs across these 20 systems in the period radius diagram. The total TKS sample has closer to 100 test systems, but for the purposes of divvying up exposure time among all of the TKS science cases, these are the 20 systems that explicitly have the sort of atmospheres label. And you can read more about how we split them up in Ashley's paper. That's not to say, though, that there aren't other systems in the TKS sample that are amenable to atmospheric characterization. And we, working on the atmospheres side of things, have our eyes on about 20 more planets that would probably be pretty attractive candidates for follow-up. But still, the TKS atmospheres sample itself still covers a good range of planet orbital period and equilibrium temperatures, with the majority of the planets falling in the sub-Neptune regime. So how did we choose those 20 systems? So we wanted to identify planets that spanned a range of stellar effective temperature and insolation flux, while giving special attention to planets with the potential to fill in sparsely sampled regions of parameter space. So we divvied up TOIs alongside confirmed planets and placed them into bins along 3 axes: planet radius, stellar effective temperature, and insolation flux. We then ranked targets in each bin according to a metric that intended to strike a balance between efficient mass measurements and atmospheric prospects. So here is sort of a visualization of that binning procedure, where I've plotted planets in the TKS atmosphere sample alongside confirmed planets. And all planets shown here are between 1.6 and 6 Earth radii, so not showing any giant planets at the moment. The y-axis has stellar effective temperature, and the x-axis is planet insolation flux or equilibrium temperature. And then the color bar indicates the transmission spectroscopy metric from Kempton et al., which is essentially just a JWST SNR proxy. And so this figure is a little busy, but the main takeaway here is that we naturally identified Sub-Neptunes orbiting G-dwarfs as a fruitful regime for atmospheric follow-up, since these planets have expected Doppler signals that make their mass measurements feasible with high res, while their bright hosts also make the observations economical. And here I just want to call out by name 2 G-dwarf hosts with transiting Sub-Neptunes that are particularly amenable to atmospheric observations. I'm showing the same period radius diagram as from a few slides ago, now zoomed in on the Sub-Neptunes. And this time I've highlighted TOI 509.1 or HD 63935b and TOI 133901 or HD 191939b. So TOI 509 and 1339 are both multi-planet systems with forthcoming confirmation papers where we've measured the inner planet's mass to greater than 5 sigma precision. And the papers are on their way, so definitely keep an eye out for those. And maybe if you're thinking about proposals in the future, keep these TOI or HD numbers in the back of your mind. So in the last slide, I highlighted 2 TKS atmosphere systems that are essentially fully characterized, but how are we doing in terms of measuring these precise masses that we need across the board? This plot shows the planets of the TKS atmosphere sample with mass measurement precision on the y-axis and the number of high-res observations obtained so far on the x-axis. And the color bar indicates the projected exposure time required to achieve a 5 sigma mass based on how our RB models are doing so far. You'll notice that some of these planets are dark, meaning that they have a long way to go before they bubble up above that 5 sigma threshold. But the picture for some of these planets might not be as bleak as it seems, since poor mass measurement precision here could be, in some instances, attributed to model misspecification. So in some cases, we haven't yet done a full characterization of the stellar activity signal. For example, modulo all of the modulo the discussion we heard earlier about overfitting, we could train a Gaussian process on complementary data like activity indicators in order to model out the correlated noise. And in addition, I'll touch on this at the end of the talk, but we've identified several systems where period ambiguity from the test photometry makes it difficult to correctly model the velocities. So cycles 3 and 4 will be especially helpful with that. Okay, so zooming out, this is the same plot, but of mass measurement precision versus number of observations, but now for the entire TKS sample. So we're making good progress overall, and about a third of all TKS systems have at least one planet with a 5 sigma mass or better. And the survey is continuing to collect data. As I mentioned earlier, we're on Sky this semester for close to 60 nights. So more to come. Okay, and looking ahead, this is a preliminary mass radius diagram of what the TKS sample will look like in the mass radius plane. So where planets here are colored by equilibrium temperature. And the TKS sample spans a range of host properties, orbital architectures, and from this plot, you can see it also spans a range of planet bulk compositions. And I've also drawn sort of special attention to the Sub-Neptune regime, because this is where most of the TKS atmospheric targets land. So in the next slide, we're going to just zoom in on that box. So the same mass radius diagram, but now zoomed in on sub-Neptunes. And planets in the TKS atmospheres program are the stars, and planets with atmospheric observations already in the literature are the large circles. And with this, I just want to highlight that, as a lot of people on this call know, the sub-Neptune regime is host to a confluence of degeneracies and models of bulk interior composition. And measurements of atmospheric metallicity may help inform these models and break the degeneracy. And this could potentially open the door to painting a clearer picture of sub-Neptune formation scenarios and potentially reveal the physical drivers of the diversity we see in sub-Neptune bulk density. Furthermore, as the mass radius diagram continues to fill out in the sub-Neptune regime, the larger sample size will enable statistical analyses, as we've started to see already before in the form of probabilistic mass radius relations. Okay, and finally, earlier I alluded to this, but I just wanted to comment that the TESS extended mission cycles 3 and 4 are going to help the model misspecification issue that I mentioned earlier with additional TESS photometry. So we've identified multiple systems where events that are actually probably single transits have been paired with spurious transit-like outlier events and have triggered a 2-transit candidate detection, or where single transits of similarly sized but distinct planets have been matched together, producing incorrect ephemerides. So as TESS continues to follow up coverage of the northern sky in cycle 4, we'll be equipped with additional photometry, which will hopefully lend insights to these instances of period ambiguity and reveal the orbital architectures when combined with our, by then, 2 years of spectroscopic data. So and also the other benefit, in addition to hopefully providing some missing puzzle pieces for the orbits of the orbital architectures of these systems, the additional photometry will greatly refine the transit time predictions, especially important for smaller planets with lower SNR transits. And this will, enable scheduling of space-based spectroscopic follow-up with JWST in the future. Okay, so I just want to end with a takeaway slide here to say that TKS is on its way to measuring the masses of attractive systems for atmospheric follow-up, and to remind you the names of 2 fully characterized multi-planet systems ready for follow-up right now. That's TOI 509 and TOI 1339. And just another advertisement to go check out Ashley's paper on the archive and tune in for her talk tomorrow. And yeah, that's all I have. So I'm happy to take any questions.
Great, thank you, Joey, for a wonderful talk. I will start to ask questions myself first. So you mentioned that TKS has been taking about 100 preliminary masses for TESS small planets. I remember this morning when Jessica Luna was given a talk about helium outflow with HET, she said that in the north, the mass measurement is a lot behind from the planets in the south. I'm wondering, is there any plan to share preliminary mass targets with atmosphere working groups out there? And so they have targets to observe.
Yeah, we have been in contact. I think TKS has tried to be pretty communicative in the TFOP community in terms of which targets we're monitoring and communicating with other teams in the south and the north in terms of sharing data. I think one goal on the horizon here for the atmospheres program is to produce sort of a catalog paper, writing up the masses, even if they're still a bit preliminary and under that 5 sigma threshold, for all of the planets in our atmospheres program. And so hopefully once that's made available and the data is made public, then people can run with it then. So that's hopefully coming up in the near term. But in the meantime, yeah, if you're another RV group and you have a specific target that you want to follow up, or you're very interested in, definitely feel free to reach out to TKS, and we're always happy to collaborate.
Thank you. I think the community will be really glad that you're really willing to share data and communicate. So I understand for you, when you select the sample, you're mostly focused on good for mass measurement and atmosphere measurement. Do you plan in the future try to make the selection process easier to correct for selection bias if people eventually want to do statistic on your sample?
Yeah, the selection process, we tried to do it as systematically as possible. And of course, just the imperfections of running a survey and we always kind of, it was never as automated as we quite hoped. So I think Ashley's paper, what it does at least is lay out in very clear terms all of the assumptions and decisions and fine tuning by hand that went into the selection function. So if there isn't sort of an analytical way to account for the bias in our selection function, at least all of the kind of asterisks are noted in Ashley's paper. So.
Great, thank you, Joey. Our next speaker would be Madison Brady, a first-year graduate student from University of Chicago. She will be telling us about all the updated progress from MAROON-X.
Hello, everybody. My name is Madison Brady. I'm a first-year graduate student at the University of Chicago, and as was stated, I am planning on providing you all with an update and some preliminary results of a survey we've been doing with MAROON-X to find precise mass measurements of TESS's M-dwarf planets. So just to start, I want to talk a little bit about why we're specifically looking at M-dwarfs. I'm sure a lot of you are already familiar with this, but M-dwarfs provide us a golden opportunity to discover rocky habitable planets. First of all, M-dwarfs are very small, both in terms of mass and radius. So the actual signals of planets around M-dwarfs are much larger for a given planetary size. In addition, M-dwarfs are extremely common and abundant in the universe. So just numerically, there will be more planets around M-dwarfs because there are more M-dwarfs. And thirdly, the habitable zone around M-dwarfs is far closer in than it is around solar type stars. Thus, we're more likely to observe habitable zone planets around M-dwarfs via processes like transit. However, unfortunately, we can't just look at M-dwarf planets and directly apply any conclusions we can make about them to planets that we find around other types of stars. This plot on the right shows that planets in the habitable zones of M-dwarfs tend to intercept a much larger amount of XUV flux than a planet in the habitable zone of the sun. This is for a couple of different reasons. First of all, M-dwarfs emit a higher fraction of their radiation as XUV flux. And second of all, M-dwarfs tend to have a longer early active period than solar type stars too. These two factors together can result in M-dwarf planets having different atmospheres, perhaps more eroded atmospheres than planets around solar type stars. In addition, the actual formation environment around M-dwarfs could be very different than that around FGK stars. This plot on the left shows how the semi-major axis distribution of planets around different types of stars seems to be different, with planets around earlier type stars seeming to be further out. The paper itself states that this could be due to different co-rotation radii of the host stars. In addition, the protoplanetary disk around M-dwarfs is likely to be of a different mass than the disks around other types of stars, which could also result in a different distribution of properties of the M-dwarf planets than around solar type stars. And thirdly, I want to bring up the possibility of the snowline distance. So this, as you can see in these two plots, the snowline distance around M-dwarfs is a bit closer in than it is around earlier type stars. For those of you who aren't familiar, the snowline represents a place in the disk at which volatiles tend to condense. So planets that form on one side of the snowline will tend to be formed of different types of things than planets on the other side, just in general. So if we can say that M-dwarf planets have a different semi-major axis distribution, perhaps a different mass distribution, and the snowline is in a different place, it's almost certain that M-dwarf planets systematically will differ from planets around solar type stars. So overall, just to kind of reiterate, the major questions that we're interested in looking at here are, what are the properties of low mass planets around M-dwarf stars? What are their compositions? What are their core mass fractions? What's their water abundance? Are these planets diverse or homogeneous in terms of these properties? Do these properties differ significantly from those around FGK stars? And finally, just as a sort of future-facing question, which planets would be good targets for atmospheric characterization? In order to answer these questions, we're using the MAROON-X instrument, which is an extreme precision radial velocity spectrograph at Gemini North. It has a 500 to 920 nanometer coverage, which is like kind of a visible to red wavelength range, which has specifically been chosen to look at M dwarfs and their radial velocities. So far, it has already been able to perform with sub-meter per second RV precision on some targets, and some science data has already been published from MAROON-X, and it has been open to the community for observations as of the second semester of 2020. So in general, our surveys, we'd like to perform RV follow-up of planets orbiting nearby M dwarfs with the intention of finding a 5% mass error on an unbiased sample of planets, allowing for measurements of their core mass fraction, constraints on their water content, and insights into the mass distribution of these rocky planets. Below, I show a mass radius plot with a TRAPPIST-1 planets overplot and some lines that show different planetary models of different water to rock ratios. I don't include this plot as an effort to tell you guys what the mass and radius of the TRAPPIST-1 planets are, but rather to show you how a precise measurement of mass and radius on a planet can allow you to actually start to constrain things like the water to rock ratio. Though of course, a lot of these models are very highly degenerate. So to select our sample, we have a volume limited group of M dwarfs observable from Mauna Kea with transits observable via TESS. Currently in this sample, there are 16 new or insufficiently characterized planets with radii consistent with those of rocky planets and visible magnitudes less than 16, which is what we've decided to set as our arbitrary cutoff in terms of brightness. In this plot here, you can see the red points actually mark our MAROON-X sample, and the blue points actually indicate points of small planets that that have a limiting magnitude of 11. My general idea here is to show you that the MAROON-X survey is allowing us to probe a very interesting area of parameter space of much smaller and much dimmer stars. Just to show you guys that MAROON-X has been successful, there's already a bit of published data or soon to be published data out from MAROON-X. The first example I'd like to bring up is GLISA 486b, which is a published paper that used MAROON-X data in combination with some other instruments to achieve a 5% mass error on this nearby sort of super Earth. In addition, uploaded to the archive earlier this week is a paper that used MAROON-X data in combination with some other instruments to achieve a 10-ish% mass error for the LTT 1445 planets. Moving forward to data that has yet to be published or really looked at, we have also looked at some other systems. These three systems I've included on the same slide because all three of them have been observed in the past with radial velocity. However, we have chosen to look at them again just in an effort to really beat down those error bars. So these three systems are TOI 488, TOI 562, and TOI 732. In all three of these cases, we have been able to improve the precision of the mass measurements on these systems, but have been unable to find any conclusive evidence of signals that would indicate any additional planets that have not already been discovered via these other papers that I have cited on this slide. However, we have looked at some new systems that have yet to really be looked at. The first one I want to talk about is TOI 1450. Just in general, on the next couple of slides, if the name of the if the title of the plot is bolded and underlined, it's a specific test signal that has been observed. So this plot here is TOI 1450. We were actually able to get an observation of the test signal, though unfortunately the planet has a very inconvenient, almost exactly 2-day orbital period. So we haven't really been able to fully characterize the full spread of the phases of this orbit. However, we are planning on observing this system in the future to really help us with this mass characterization. However, even with this data, we have been able to find some preliminary evidence of 2 additional signals of possible non-transiting planets in the system. And if all of these signals are roughly coplanar, we could possibly have a 3 Earth kind of Earth to super Earth mass planet system. However, all 3 of these planets fall well within the inner edge of the habitable zone. In addition, we've also looked at TOI 2013. This is another system with a single known transiting test signal. We have been able to find a pretty decent measurement of this, about 10% mass precision of this planet. In addition, we found evidence for an additional very strongly eccentric 14-day signal. It appears that this system has also been examined a little bit with Carmina's. They have a poster up that you can check out if you want to see what their data looks like. Then finally, perhaps the saddest, we looked at TY2142. As you can probably see from these plots here, it doesn't look great. We found some evidence of maybe a 14-day signal, but we've had a lot of difficulty finding a signal finding any sort of real amplitude in the TESS period and time of transit. And even when fitting out any additional signals, we only get about a 50% mass error. However, looking a little deeper into this system, it turns out that this target has yet to be validated with ground photometry. So it's possible these observed transits that have been seen in the TESS data may be from some sort of background object. Just to sort of kind of help build up my case here, it does seem like there is some centroid offsetting in the TESS vetting report. And in addition, this is a TESS image of the target. The little black X represents the actual target that we observed with RV. And these little red circles indicate other possible sources from Gaia. And given the TESS mass kind of encompasses this whole area, it's possible that perhaps some of what we see is from a background source. So just in general, to place all of these planets in context, I have produced my own mass radius diagram with some overplotted lines just representing different general planetary compositions and all of the different individual planets that we have on top of it. Each planet point is colored according to its effective installation compared to the Earth. So I kind of want to point out three major groupings on this plot. First, we have this extremely narrow range of planets that appear to all basically have a 1 sigma mass radius consistent with an Earth-like composition. Secondly, we have these two planets up here, which have much larger masses and radii. And third, we have this planet that doesn't really seem to fit in with anybody else with very large mass and radius error bars. Now, here is my effort at trying to disentangle this in a sort of preliminary fashion. First of all, we somewhat obviously have the group of Earths and super Earths with that sort of compositions consistent of 1/3 iron, 2/3 rock. Second, we have these Sub-Neptunes, which have much larger radii and much lower bulk densities. And then in between them, we have like what looks like maybe preliminary evidence for the actual radius value that we would expect to see in a sample of exoplanets like this. Though, of course, with the small number of systems that we're looking at, it's hard to say anything statistically conclusive about it. And then this last point here is TOI-2142, which, as I stated previously, might actually be misplaced. And then in general, in the future, our interests with these systems are to really try to further explore these models for these Earths and super Earths to really try to nail down what are the differences, what are their bulk compositions, et cetera, et cetera. And also to look at more systems that are included in our sample. As you can see, this is not all of the sample, all of the planets that fell within our sample that I was describing earlier. We're hoping to look at more of those in the future. And then finally, we're actually going to revisit some of these systems to further improve the measurement precision on each of them. So this is I'll just leave you guys on my summary slide. Please feel free to contact me if you have any questions. And that's it. Thank you for listening to my talk.
Great, thank you for the talk. The instrument is really impressive. Great to see all the new results come out. So yeah, we have a few questions for you on Slack. I'll start with Dax Felice. Question for you. What is the limit MAROON-X can observe for phantom dwarf targets? Can it reliably observe as faint as 14 to 17 TESS magnitudes?
We have been able, I think the dimmest and most impressive target we've been able to look at so far is TRAPPIST-1. I would say that kind of represents the dimmest target that we can look at in the M dwarf range. Unfortunately, the instrument is very specifically geared towards looking at M dwarf, so the limiting magnitude is, I guess I would say the limiting magnitude is lower when we're looking at earlier type stars.
Great, thank you for that. And the next question would be from Emily Saffron. Can you make a clarification on what do you mean by unbiased sample in early when you said talk? What
Absolutely.
Actually account for? And I think she also specifically asked you about do you include planets with longer period from non-transiting detection methods?
We are currently just specifically looking at transiting planets that are within this volume limited sample. Our intention is, of course, there's going to be some limitations based on the actual magnitudes at which we can observe, but our intention is ideally the actual like volume limited sample within 30 parsecs of us doesn't like differ significantly in terms of planet properties or planet mass properties than other samples would. So that's what I mean when I say unbiased, is we're kind of hoping to get a concrete understanding of these planets specifically around M dwarfs without any biases creeping in. Like we did not choose to look only at systems that had planets of certain radii. While I do mention that 16 new or insufficiently characterized systems have planets of this radii, we are also planning on including other planets in the system. So we are planning on including a few Sub-Neptunes. As you can see in the last plot, there are already a few that are kind of crept in. Does that clarify things?
Yeah, that makes sense. Yeah, I think the idea is that you unbiasedly select sample from what test.
Yeah, because ideally, you know, since the test planets are transiting, like the actual chance of a planet transiting is not systematically related to the actual properties of the planet. Though of course there are going to be biases due to the actually length periodicity of these systems. So that's going to mostly, I think, just prevent us from being able to draw conclusions about systems with very long periods, and instead mostly focus in on these like close-in M dwarf planets.
Great, thank you very much. I think there are additional questions on Slack, and go ahead and answer them. And so our last science talk of the day is going to be from Tianjun Gan from Tsinghua University, China. He is a graduate student and a proud SG1 member. He will tell us about solar twins and from TESS.
Okay, thank you, Chelsea. So I hope everyone can see my screen and hear my voice now. So great. Hello, everyone. My name is Tianjun Gan, a third-year graduate student from Tsinghua University. So it's my great pleasure to have a chance to present my recent work here. Today, I'm going to talk about hunting for test planets around the solar twins. So I will start with a short background about why we want to study planets around the solar twins, including a brief introduction to the solar depletion pattern. Following with some discussions about a recent confirmed planet, TOI 1055b, which is a warm sub-Neptune transiting a solar twin. And finally, I will briefly overview the scientific opportunities regarding solar twins with Kepler and TESS. So the first question is, what does solar depletion pattern mean? So this plot shows the elemental abundance difference between the sum and the mean values of 11 nearby solar twins as a function of the condensation temperature. So the solar twins are defined by their extreme similarity to the sum in fundamental spectroscopic properties as shown here. So in this plot, each point represents a specific element, while this red solid line is the best fit piecewise model to this data. So Melendez et al. 2009 found that with respect to these 11 nearby solar twins, our sum shows a depletion in refractory elements whose condensation temperatures are higher than 1300 Kelvin when compared with volatile elements whose condensation temperatures are lower. So this overall deficiency is what people call the solar depletion pattern. And generally, this pattern is quantified as a correlation between the refractory elemental abundance and the condensation temperature, which is also called the TC slope. So although there are still some debates on whether this pattern is real or not, currently there are several hypotheses that may be able to explain this phenomenon, and 3 of them are related to planets. So the first one is the Rocky body formation, which suggests that the refractory materials may be locked up in the terrestrial planets or the asteroid belt in our solar system. And moreover, recent work from Booth and Owen 2020 shows that the trapping of dust due to the gap opened by a forming giant planet could also result in this feature. So under this hypothesis, the formed gap will prevent the dust outside the giant planet's orbit whose mean compositions are refractory materials to be accreted by the host star. However, at the same time, it still allows the gas outside to move in, which leads to the overall observed deficiency. And then additionally, it has also been supposed that this solar depletion pattern may be caused by the planet engulfment, which replenish the stellar refractory materials in nearby solar twins. So in short, the first two processes reduce the refractory elemental abundance in our sun, while the final one enhance the stellar refractory materials in other solar twins. And finally, it has also been supposed that this solar depletion pattern may be caused by the galactic chemical evolution. So it manifests as different correlations between the elemental abundance and the stellar ages, as shown in this plot, which is expected to have an effect on the final values of the TC slope. However, recent work from Bedell et al. 2018 performed a detailed line-by-line differential analysis to high signal-to-noise ratio Hubble spectrum of 79 nearby solar twins, and they found that the TC trend still exists after correcting the age abundance effect as shown in this plot, which hints that the GCE is probably not the key source of the refractory depletion. So through RV surveys, previous solar twin samples are limited in planet detections, especially for small planets like our Earth. However, as a whole sky transiting survey, TESS provides us a good chance to increase the number of planets around the solar twins to help us further investigate this problem. And here is an example. So TOI 1055b is a recent confirmed warm sub-Neptune transiting a solar twin. So here I'm showing the phase-floated TESS light curve, Hubble's radial velocities, along with their best fit transit and Kepler model. So our joint fit reveals that the planet has a radius about 3½ Earth radii with a mass of around 10 Earth mass. And it is also worth noting that this is the 5th brightest sub-Neptune systems in the sky up to now, which is definitely an attractive target for further atmospherical characterizations. So now an interesting question would be, does this star also show a similar depletion pattern like our sun? So now we are looking at the TC slope distribution of the aforementioned 79 solar twins started by Bedell et al. 2018, which has already corrected the stellar age effect. So here for a negative slope, it means an anti-correlation between the refractory elemental abundance and the condensation temperature for individual stars, which corresponds to a depletion feature. Otherwise, it corresponds to a non-depletion feature. So interestingly, unlike our sun, this star likely belongs to the non-depletion group, as shown as a green line here, even if both of them host Loki bodies. So here, in this case, the Loki body is the Loki core inside the sub-Neptune. So it hints that the Loki body formation may not be the key reason for the depletion pattern. But of course, we cannot draw any conclusions from a single target. Then are there any existing solar twin samples with Loki planets around? Yes. So the California Kepler survey has already collected around 1,300 Keck spectrum of Kepler stars that host more than 2,000 planets. So after setting some criteria on both stellar and planet properties, we filtered out 36 solar twins with confirmed Loki planets around, which allow us to test the first hypothesis. That is to say, to check whether Loki planet formation plays a role in the solar depletion pattern. And here is what we found. So this plot shows the mean abundance of these 36 solar twins with Loki planets as a function of the condensation temperature. So these abundance are derived by Brewer et al. 2018, who took use of the spectroscopy made easy package. So this blue solid line is the best fit linear model to this data, while the shaded region is the 1 sigma confidence level. So our result is possibly consistent with the piecewise model from Melendez et al. 2009 I mentioned at the beginning of my talk, which is based on a mixed planet sample. So for most stars in Melendez et al. 2009, they do not have confirmed planets yet. However, our selected CKS sample is a pure Loki planet sample. So it once again hints that the Loki body is probably not the dominator term in the solar depletion pattern. But our preliminary result is still limited by the accuracy of the abundance measurement. So currently we are performing a detailed line-by-line differential analysis to this high-res data and double check our result. And then let's go back to TESS. So what about TESS? Can we build a similar sample to study this problem? So the answer is definitely yes. So this plot shows the effective temperature and the surface gravities of all TOIs after removing the known false positives. So these stellar properties are taken from TESS version 8.1. So among them, we identified 100 potential solar twins marked as red dots in this plot with this selection criteria. So we call them potential solar twins because we do not have the metallicity information in hand currently. So compared with the previous selected CKS sample, the TESS provides us a large number of bright potential solar twins with planet candidates whose V-band magnitude are smaller than 11. So these stars can easily be confirmed as real solar twins with spectroscopy facilities on small telescopes. For example, NRES on 1 meter LCOGT telescope. And after that, we can also achieve precise and accurate abundance measurement with the high signal to noise ratio spectrum taken by facilities on larger telescopes like HARPS. And another thing I want to mention here is that there is a peak at around 13.5. So these stars are mainly contributed by the recent quick look pipeline faint star search, which has already enlarged the total potential solar twin sample by a factor of 2. And we expect that it will identify more such cases in the near future. And then additionally, from the planets aspect, TESS also provides diverse planet candidates with different radii. So here I'm showing the radius distribution of all planet candidates hosted by our selected potential solar twins. So we can see that except for the Loki planet candidates, there are also plenty of giant planet candidates hosted by potential solar twins, which the previous CKS sample do not have many. So to summary, TESS brings us a good chance to simultaneously test whether Loki planets or giant planets plays a role in the solar depletion pattern. And furthermore, in the extended mission, TESS could detect long period planets around those potential solar twins, of which, especially for planets around the bright stars, of which the mass are likely to be measured. So it will allow us to further explore the potential relation between the total planet mass in a system and the TC slope values. And I think that's all I have today. So I will just leave my summary here and happy to take any questions. Thank you very much.
Thank you, Tianjun. Jessie Christensen has a question on Slack, although she said it's not necessarily especially for you, but I just want to see whether you have any opinions on that question. And the original question is that why does chromium decrease with time in galactic chemical evolution? And why does it behave differently from the other elements compared to iron? If it's not in your field, feel free to say so.
Yeah, yes, actually, I'm not an expert on stellar astrophysics, but I think that's something related to nuclear physics, I guess. But I'm sorry, I don't have the answer yet, but
no
we can chat out after offline.
Yeah, great. So next we'll go to a question from Kevin Schruffman. Sun-like star is fully convective for the first 20 million years of its evolution. So any accretion depletion that occurs before that time would be well mixed with 1 solar mass of solar composition material. How many Earth masses of material need to participate in the proposed accretion depletion process to produce and observe the TC slope in the photosphere of a mature solar twin?
Oh, I see. So that's a great question. So I think previous work from Chambers 2010 has a result. So in the right panel, so I hope everyone still can see my screen. Yes, okay, great. So in the right panel, I'm showing the expected solar abundance after adding 4 Earth masses, Earth and chondrite-like materials into the solar convection zone. So these dots are the theoretical models, where this solid line is the previous observational result from Melendez et al. 2009. So it shows that after adding 4 Earth masses, Earth and chondrite materials into the sun, it can bring our sun up to the mean levels of the nearby solar twins. So perhaps the missing mass is around 4 Earth mass. But I'm not sure, are there any recent results from any other people? Yes, this is a result 10 years ago.
Okay, great. Last question for you from Vadan. Sorry, I would not be able to pronounce your last name accurately. What about the cores of giant planets? What if they are made of rocks? What would be their contribution to the TC trend?
Yes, that's a good question. So, of course, I agree that there is a rocky core inside the giant planets. So then I think to break the degeneracy between the rocky planets formation and the giant planet formation, first we need to have 2 different samples. So for a sample, one sample with only rocky planets, and the other sample is with giant planets, and choose, and then we can check the difference between their host star TC values.
Great, thank you, Tianjun. And I also want to thank all the speakers for this session. Feel free to go on and interact with other people on Slack. And I just want to remind everyone that for today, we still have an off-topic talk. I think we're going to push that to 6:20 p.m. ET, just to give everybody a break. The off-topic talk will be about the role of art in science communication. And they will be talking about the new TESS trifle posters. And we will still be using this Zoom link for the off-topic talk. So I'll see everyone in 10 minutes. Thanks.
Hello, Kaitlyn.
Hi, Avi.
You can go ahead and check your share your screen. Check that any slides you're able to share them, and make sure they have the connection. Okay. Hello, Joby, and hello, Thalia. We will start at 6:20. I should say 6:20 East Coast time and 3:20 West Coast time. We're taking a small break to let people get some air after the series of science talks.
Great. Can you hear me okay?
Yeah.
Thalia and Joby, you guys want to do a sound check?
Yeah.
So,
Can you hear me?
Yep.
Okay.
Joby?
Can't hear you.
Can't hear you.
Check
No.
1, 2. Can you hear my?
Yep.
Can you hear me with my mic now?
Yes.
All right. I just gotta break these bad boys out.
Great.
So okay.
So looks like we're all set. We'll just wait for 6:20, or in your time zone, it's 3:20. So anyone on the audience listening, we will start at 6:20 East Coast, 10:20 UT. Feel free to take a break, go get your coffee, tea, or stronger beverage if that's your likeness. And we'll start in 5 minutes or 6 minutes.
Hey, folks.
Hey, Jen.
Okay, so hello everyone. To remind you, this will be the first of two what we are calling off-topic talks. And off-topic talk is something that is not about test science, but interesting to the audience of this conference. And now we have with us Kaitlyn Soares, Joby Harris, and Thalia Khan, and apologies for any mispronunciation. They are from JPL in California, and they are part of the team that is producing the travel posters, Exoplanet travel posters, which we have seen for several years now. And we asked them to share their experience with us and the process that they go through in producing those posters. So I'll just hand it to them, and you can just go ahead.
I think we're waiting 9 minutes, right? This kicks off at 6:30 is what we told people.
We were supposed to start at 6:15, but we pushed it a bit because the session ended a bit. We went a bit over time. So, but officially on the website and everywhere, it's 6:15.
Oh, my bad. I communicated that incorrectly earlier today. If you guys have a few moments to spare, I would maybe request that we wait 8 more minutes, because I definitely told people repeatedly it starts at 6:30, and I apologize for that.
Yeah, let's
no worries. Yeah.
Let's take a few more minutes.
No problem.
Avi, you got a little warm up.
Yeah. So how was it going in California? Is it still a lot of ash in the air?
A lot of ash, you said?
I hear there's a lot of fires in California, and
I haven't really seen any or smelled anything for a little while in LA here where we are in Los Angeles, but it seems to be pretty bad further up north.
It's more.
Yeah, it's kind of the start of our season now, so I'm sure we'll get some stuff in LA soon, unfortunately. There are some photos, you can probably Google this, but this is before my time at JPL. I've only been at JPL for about 3 years. Joby, I think you might have been at the laboratory at this time, but there are some photos of a fire that came very close to JPL a few years ago. That was very close to our facilities.
Yeah, that was every year, as you know, we get fires. As to whether or not how close they get is another issue. It tends to look worse on the news than in reality, but last year was
everything looks worse on the news than in real life.
Exactly. And but last year was probably, in 20 years I've been here, the worst that I've experienced in terms of smoke. So we were doused for a good solid month with some terrible air quality. I mean, it was super orange outside during noon. I'd never seen it that bad. So everybody went out and bought air cleaners for their apartments and buildings, and everybody just kind of stayed in for three additional months despite everything. So that's the worst I've seen with smoke and ash last year. Hopefully they're implementing new things government-wise to help prevent a lot of the fires. So we'll see if that works this year. But I haven't seen any in LA yet. Have you guys? Okay. Yeah. So far it's just kind of a lot of the forests up north. But so
my parents live outside of Boston, and they said that they've been getting some wildfire sunsets. So I think it's affecting them more than it's been affecting us.
There was a bit of smelling the fire without seeing them.
Yeah.
So maybe one more thing for the audience. We do plan to take some questions at the end of this talk, and we can simply use the general Slack channel for that. So if during the talk you have some questions, you can put it there, and we will try to get to as many questions as time allows.
Jen, did you say in our email before that you'd be fielding the questions?
Yes, so I will keep an eye on the
Perfect.
chat. I'm gonna not interrupt you folks during your actual presentation. I'll hold everything till the end and then moderate and bring things up one at a time for you.
Sounds good. Thanks.
How long has this conference been going on? How long have people been online?
This
And
is
whatnot?
day 2.
Day 2?
This is yeah, this is what we call like a standard full week conference, like Monday
Nice.
to Friday.
Oh, Monday through Friday, and then for how long during the day? How many hours?
Well, since this is online and only online, it's a bit different than in an in-person conference. We would just go roughly 9 to 5 every day, more or less. And now we decided to do 2 very separate sessions during the day. Each one is about 2.5 hours long. And the goal is that to try and that in every time zone, at least one of the session will be in, let's say, reasonable local time.
Yeah.
Of course, there is no perfect solution for that problem. There are only approximations.
Right.
We chose the approximation that worked best for us.
Got it. No, yeah, this seems to be a well-rounded time for most people.
So we have another off-topic talk tomorrow, and it will be in a much earlier time in the day to catch another time zone.
No problem.
I think all of our TESS adjacent talks ended up being from JPL folks. So clearly there's a good synergy between lab and what TESS is doing, or what the TESS audience is interested in.
That was totally unplanned. But
well, Thalia, were you there when we went out to Goldstone? Kaitlyn, I know you were there.
I don't think so.
We went out to Goldstone and had the privilege of standing underneath the dish when it was first aimed at TESS, and all the alarms came on and the dish started moving. And we were just excited to stand under it while it was moving. And then they said, this is this first point to TESS. So that was really exciting.
That was really neat. Yeah.
And everyone's looking at the clouds like it's up there somewhere.
So just to make sure for the audience, if what Joby was referring to is that one of the communication with TESS itself, that was it's done, I think one of the stations is through JPL or through one of the dishes out there in that area.
Yeah, the Deep Space Network.
Yeah, the Deep Space Network. So the dish needs to point to TESS, wherever TESS is in the sky, and then start receiving data.
Exactly.
All those pixels.
Yeah, and it was a good drive out in the middle of nowhere to get to these dishes, that's for sure. So it's really out there. It's worth it. So if anyone's near a Deep Space Network station, it's worth a trip.
But don't go climbing on the dish.
Yeah, don't go climbing on the dish. I've tried it. It doesn't work. No, I'm kidding.
Don't interact with the donkeys, the burros.
Yeah, the
lots of animals out there.
Lots of wildlife around it. I think even a bird I think there was a nest in the dish that was pointing to TESS, and that bird was probably used to it. But
it was a hawk nest. Yeah, it was pretty interesting.
We'll send you pictures, actually. Beautiful. Right.
Okay, it is 6:30 by my watch. I very much appreciate the minor delay just to make sure we don't cut people off who were very, hoping to catch the beginnings of this. But yeah, so feel free to take it away, folks. For anyone who joined recently, as Avi mentioned 10 minutes ago, this is our first kind of TESS adjacent talk, and we'll be learning about the work that goes into designing, creating, distributing the variety of exoplanet posters that have come out of NASA over the past years, and the broader role of art in science communication. So please go for it.
All right, thank you. Okay, well, welcome everyone. Very glad that you all can join us. So today, Kaitlyn, Joby, and I will be talking about the role of art in science communication. You may have worked with us before in the past, or you may be interested in working with us in the future. So we're here to talk a little bit about what we do and some exciting products that are being released and some exciting things that we've worked on. So if we can go to the next slide. So I am Thalia Khan. I am a public outreach specialist for NASA's Exoplanet Exploration Program Office. I do public outreach. I communicate the science of exoplanets to the general public. And I will toss it over to Kaitlyn to introduce herself.
Yeah, thanks, Thalia. I'm Kaitlyn. I work with Thalia in public outreach at JPL. Also, my specific focus is in astrophysics. So I represent missions or communications for missions such as NuSTAR, SPHERE-X, which is an upcoming space telescope, a few others as well, the recently retired Spitzer telescope. So I lightly touch exoplanets, and then also astrophysical phenomena is something I'm really passionate about explaining and communicating to the public through art. And we also have Joby on our team.
Yep, I'm Joby Harris. I'm a visual strategist. It's an interesting title. I'll be talking a little bit more later about what that is. And I just support JPL and NASA with design strategy, with artwork, and anything that helps them communicate with each other and the public. So we're excited to kind of hang out with you a little bit today.
Sorry, my mouse is a little jumpy today. So this chart kind of breaks up how communications is siphoned in NASA. So we have communications teams that are pretty much split up into a media side and a public engagement side. On the left, on the media relations side, those folks handle press releases and press conferences, which I'm sure that you've seen for launches and big science news that comes out of NASA, graphics and videos in support of those releases and features. And they interface with journalists and other media who are interested in covering stories and working with NASA to spread our news. On the public engagement side, which is what Thalia and I touch, we have visualizations, we produce social media posts and media for to accompany those posts. We go to events and conferences, anything from South by Southwest, which we did this past March, and Comic-Con, which we've done in past years, to science conferences like the TESS conference, AAS and AGU. We produce print and digital products, multimedia packages, websites and features, and more graphics and videos. So these two groups really work together to spread the news of the day and then bigger information about what NASA is doing in bigger storylines as well.
And so, although you guys may not have heard of us, you may have seen our work. So we are the group that is behind these beautiful posters that highlight different worlds that we would potentially want to explore. And Joby was the fantastic artist behind a lot of these posters. So we just wanted to put into context who we were, why we're here talking to you guys, the exciting things that we work on and the exciting things that are to come. Next slide. So like Kaitlyn mentioned earlier, we do a lot of public outreach and communicating science to the public. One of the things that we do is we sort of tell the thematic story of exoplanet science to the general public. And part of that is running the thematic exoplanet website. So as you can see here, this is a screen grab of our website where you can find a lot of useful resources. This is geared towards the general public. So people who don't even know what exoplanets are, they don't even know that they exist, can come here, learn a lot about them, find really cool resources, and engage with our content and your science. Next slide. And we also do a lot of public events. So these are just some images from some events that we have done in the past. We've done Comic-Con, we've done open house events at JPL where we get to feature our science, but also get to talk to the public one-on-one and really get them engaged in what we do at NASA. And then next slide. And we also, like I said before, our outreach team creates a lot of visual resources. Visuals are really important in the way that we're conveying science to the general public. Think of how you would explain it to your niece or your mailman or someone who isn't science initiated. So we have, we do a lot of VR products, literally placing people on different worlds through VR goggles or 360 videos. We create infographics. This one specifically in the middle of this slide explains the life cycle of stars in a beautiful visual way. We produce data visualization. You're seeing that on the top right of the screen. This is actually, can't really see the names here, but this is the TRAPPIST-1 system in real time showing the orbits of the planets in their order. This is part of the Eyes on Exoplanet system that we manage out of JPL, and we can embed it into different stories to tell that more visually, very much like you see major publications like the New York Times visually embed data. We do that as well. And animations. Animations are very important for B-roll in our videos. You know, how we explain through video and different multimedia the story of discovering exoplanets and their systems and stars. And I'll turn it over to Joby to really talk about, or to really go into a deep dive on the art products that we make at JPL.
Thank you, Kaitlyn. So yeah, Thalia and Kaitlyn really touching base on the importance of reaching different audiences. And so that's actually a role that I stepped into at JPL. I work in an area called the studio that sits within a larger design lab there. And our whole purpose is to help communicate these complex things to the broadest audience possible. So Thalia and Kaitlyn will normally call me or someone else in our studio to come in and sit down and look at what it is that they're trying to communicate. And then it's my job to help figure out an interesting way to do that. So I've been at the studio for about 10 years, and I'm just going to give you a little brief synopsis on what I have learned over, because when I first started working at JPL as an artist, I wasn't sure how art connected to communication with science at all. I didn't even know what I would be doing or contributing. I come from film and music, so what would I be doing there? And so after 10 years, I realized what I would be doing there and decided to kind of dig a little bit deeper into, by one, illustrating the exoplanet posters and seeing those go viral in 2015. Being a part of other larger projects there, you see a picture on the right there, that's my supervisor, Dan Goods. That's actually a light pulse sculpture connected to deep space data being received. So the spacecraft that are out there are communicating with us, and we connected that data to light. And so we have that in our lobby, so people can actually see the conversation going on between Earth and space. The dome-looking object at the top there is a sound pavilion. So we assigned every Earth-orbiting satellite a sound that you can hear when you go in there. A lot of people didn't realize what NASA does for the Earth, let alone for outer space. So we started connecting this data to sensory things, of course, visuals as well. So next slide. So that's been a part of my job, but the more that, we faced a little bit of, we faced a public that was uncertain about how art fit in with science. Could it be used that way? Is it even a natural connection? We've even faced that internally. Really not understanding the value of art connected to science and science communication. So the more that we kind of looked into it, we realized that this goes back to the beginning. It goes back to Aristotle. He had illustrators in the 1500s named Peter Apian, who would start to break down Aristotle's talks into visual form so that people could understand it. I don't think we'd be able to understand the stars without visuals and storytelling to help us understand what's going on up there. I'm going to kind of breeze through this short list here, but I recommend you take a screenshot and look up each one of these individuals. Everybody knows Leonardo da Vinci. You don't have to look him up. But some of these other ones like Maria Imart, who was an astronomer and an engraver, very early on, women were the pioneers in science and art communication, including Anna Atkins was considered to be the first female photographer, taking beautiful, still today, beautiful images of the plants and flowers that she was collecting as a botanist. But I highly recommend that you look up the last person there, W.E.B. Du Bois. He was an African-American sociologist in the late 1800s who was the earliest pioneer, one of the earliest pioneers of data visualization, how to take complex things and help people understand what was going on in the early 1900s when slaves were entering into society, what was happening there. So I highly recommend, this is just a broad stroke, but all this to say that art with science has been in stride with science since the very beginning. This is not a new conversation. Next slide. So my role at JPL and NASA, I started kind of looking in our archives, and JPL was started in the late 30s technically, and existed as a lab in the 40s to help our Army at the time, and then became a space brought into the NASA family in the 60s. But it's been around a long time. So as I dug into the archives, of course, I see a supercomputer, but then I look next to it and I see, wow, there was an artist at that time helping communicate what was going on. And at that time, it was the flight plan to the moon. So I thought, oh, that would have been my job back then. So what is the history of artists supporting science at NASA? And so next slide. Found out that there was actually an art director who goes back to 1952, who led a group of 14 women and 7 men known as the graphics group. And so they right from the beginning, there were artists involved in helping scientists and engineers communicate with each other, and especially with the public, what was going on. And in this case, going to the moon or Voyager. Next slide. Then as we got into the 60s with the formation of NASA, there was actually an art program created for one purpose, and that was to give artists access to everything that was being done, to go back and then take their interpretation of what they saw and heard and experienced and put that into art form for the purpose of speaking to people, communicating to people differently than data. They realized that not everyone had a PhD level degree. They realized not everybody had access. So could they speak emotionally to people through the arts? And so that program began in the 60s. Go ahead, next slide. In the 70s is when Ames brought in artists to help design what could the future look like, knowing that films and TV, comic books, the arts really kind of pulled people into science and engineering. Of course, teaching and teachers and schooling did that as well, but you'd be amazed. Maybe some of you were inspired by something that you watched, a film or a TV show. The 70s really brought in a lot of the artists that were involved in cultural things to what would the future look like? And they actually created studies with that. Next slide. And as I start to wrap this up, something interesting that I discovered at JPL was a computer graphics laboratory started in the 70s. Bill Gates started using a computer in high school in 1968. So this is still relatively very new technology, especially for the arts. So in the mid 70s, a computer lab was started at JPL for the purpose of helping planetary encounters, science, but they also used it for graphics and for animation, to which one of them, Dr. Jim Blinn, was attributed with Blinn's law. With, if you know a lot of 3D graphics, it's a pretty big staple in the 3D world. So I could honestly say that 3D graphics were pioneered early on by NASA at the Jet Propulsion Laboratory by this group. As Dr. Jim Blinn told me, a lot of people from early Pixar and Lucasfilm were coming to them, in Hollywood, coming to them to see what is going on here. What is this? So they were really big staples in the arts in terms of 3D and video. Next slide. And I'll breeze through these. Of course, the 80s brought in the worm logo. I think culturally, art was associated with space, and it became a cultural phenomenon in the 80s. Next slide. And that brings us up to today with the exoplanet posters going viral. You've been talking about exoplanets since the 90s. A lot of the public had never heard of them until these posters came out, admittedly, by them. And so I have seen personally through the research of seeing how art has been in stride with science since the beginning, and how it has gone full stride even today, not just with external communication with Thalia and Kaitlyn, but we've also found a niche or a place at JPL and NASA to help with mission formulation in the proposal phases, helping scientists and engineers think through their thinking, almost like therapists. You know, we help them communicate, but through the art, through visual communication. So next slide. And so I just kind of summarized this by saying, look, these are all the people that have to talk with each other. It's a lot of different people, a lot of different backgrounds, a lot of different education, you know, degrees, a lot of ages groups, a lot of diversity in terms of where you're from. I want to show you where artists live in this context. So this is where art lives. Artists live in connecting all of these people to each other, and help build bridges of communication to each other. Reason being, next slide, you know, what you're talking about is very important. So, you know, you have your data, your research, your facts, your science, engineering. Art is a powerful tool that allows all of that stuff to filter into one piece that everyone from a PhD level profession down to a child can look at and get some understanding from. So if I can replace the word artist with communicator and the word art with communication, that is the power of art in science and communication. So that's why Thalia and Kaitlyn call upon people like myself, visual strategists, to step into their projects to figure out how can we best communicate these complex things to the widest range of people possible. So yeah, I just wanted to share that. I'd love to toss it back to Thalia or Kaitlyn.
Thank you. So as Joby taught us, art and science are very important. They go hand in hand. Art is essential in communicating the science that we do at NASA, but the process isn't always as straightforward, as streamlined as people may think, right? It's not, you know, some communication specialists and some artists getting in a room and cranking out beautiful visuals. It's actually a very iterative process to create artwork. There are a lot of people involved. And so this is kind of just an outline of what that process might look like. You know, someone would have an idea, whether that be a scientist, whether that be a communications person. We would propose, you know, to management, to NASA, to produce this product, to produce this art, this piece of art. Then we would gather a team of producers, artists, scientists, engineers in order to work on creating this product. And then, you know, we would brainstorm, you know, develop a concept, and then we would go through rounds and rounds of reviews. And then we will finally get out a final product. Go to the next slide.
I want to add really quickly. So I think just from a personal perspective, I think step 3 is really the most exciting step for me, at least in this process. There is no shortage of scientists or engineers at NASA that we get to work with, really. So it's fun to get a different team together every time and hear everyone's different ideas that are brought to new projects as we progress throughout the year and create different things. So this is a really creative process. Like Thalia said, it's not a straight line. We can be in a random meeting and somebody might have an idea for a product for another time, and we'll bookmark it and come back to it at another time. But yeah, I personally just love my job so much because of all of these things, but really step number 3 is something that I really treasure about working at NASA and being able to bring these teams together. So many different people of so many different backgrounds to create something really cool.
So this process, like Kaitlyn said, is a bit messy. And here you can see, so we actually, 2 years ago, I think, produced this poster of a TESS discovery. So this is a myth. We wanted to be able to tell the story of what is happening in the system. And on the left, you can see us with some of our scientists. And then at the bottom left, you can see us brainstorming some concepts. What could this look like? How can we convey to the public what this might look like? And what is especially tricky, especially dealing with exoplanet science and other astrophysical phenomena, is we don't actually have pictures for reference. So we have to heavily rely on the observations and what our scientists and our experts tell us about, these planets, these systems, to inform what this might look like. So we work very closely with them to develop something that is scientifically accurate, but also really engaging to the public. So as you can see on the right-hand side, that is the final product. This is what we produced for the AUNIC system, and it is part of a series that we'll talk a little bit about later on. And this is just more pictures of drafts that we have come up with. And Joby, you can talk a little bit more about what this process is. But this basically illustrates that sometimes our ideas for things change. Sometimes we get new information about the science behind things that changes what these visuals might look like. And Joby, if you want to talk a little bit about the process here.
Yeah, so the design process usually starts with meeting with the team there with Thalia and the scientists. And our general understanding is, okay, it's a lava planet. So there would be lava waterfalls, or lava falls on this planet. And so the idea of, why would someone want to go there if it is a travel planet, travel poster, come here for this reason. So we thought, wow, beautiful lava, falls, and this would be crazy space train that, we don't bring as much attention to the train as much to the lava falls so that people don't get hung up in technology and things like that. So those are some of my first concept sketches there. We even got excited to hear that perhaps the lava would be blue given the science on this planet. So those are early concept phase sketches, and then we learned there would be no solid ground on this lava planet. It was just lava. So that shifted everything. Why would someone want to go to just a lava planet? And so if you can see in the middle there, it was, okay, would there be like some sort of space boat races? Sort of an extreme sport type of, it would definitely be an extreme sport type of planet to go to. That's why you'd want to go. Then that kind of got shot down. And then, well, would someone want to go there to relax and do yoga, all the colors and the beautiful lava? So, well, that got nixed as well, because it just wasn't appealing aesthetically. As a designer, we just didn't really find the idea until we started to give up. But then one of the scientists said, the atmosphere actually is made of silicate and would sparkle and reflect whatever the lava, whatever was going on underneath. So it could just be sort of this dreamland of light and sparkles. So, that would be something to experience in the air or in the atmosphere. So then we went down that. So the process is more like a dance. We're dancing with the scientist. Okay, what is the scientific evidence that you're corroborating with other scientists at universities around the world? Could it be possible for this? And then it's my job as the artist to think, no, that wouldn't be aesthetically pleasing. That wouldn't be a good poster. And then we eventually come upon sort of a middle ground where, as we came to the lava there, we developed a sort of a aerial, type of thing. And then NASA said, well, what happens when the boat stops and then they go back down to the lava? They die. So would someone go to this lava planet again to die? And we were back at square one until I put a protective bubble around the folks there. And then that seemed to solve the problem. As long as no one asks exactly what that bubble's made of, I think we're okay. Some sort of futuristic coolant. But again, this could be the art that pulls someone into the future going, there needs to be a coolant that can form a bubble that protects people from a lava planet. And then they figure out how to make that and what that is. So I just wanted to give you a little glimpse in terms of what is average dance with each poster with the scientists as we figure things out.
Right, and so it takes a lot to produce sort of extreme planets or extreme occurrences or events that happen in outer space. And in response to that, in response to all of those struggles that we had and not depicting anyone dying on a planet or, trying to also visualize the extreme planets, we actually came up with a brand new series of posters called the Galaxy of Horrors. And this really depicts all of the scary destinations in our galaxy and all of the extreme phenomena that we would, that people would probably be really interested in learning about. So I started off the series with some extreme exoplanets, some exoplanets where it rains glass sideways, planets around a pulsar, and then Kaitlyn actually took it on and she moved it into astrophysics, and she created some really beautiful visuals.
Yeah, thanks, Julia. So this is my favorite. I really like the travel posters, but I have this dark side, and I love Halloween. So I'm really glad that I was able to work on this new iteration of the Galaxy of Horrors posters. So like Julia said, the first few that she produced were exoplanet related. Last year for Halloween 2020, we expanded it into the astrophysics realm. So we looked at this galaxy on the left, MAX 2129-1, which Hubble observed. That's one of the oldest galaxies observed by the Space Telescope, and it's just old and red and dead and decaying. So we portrayed that. We used external artists for these posters, and the artist Ken, he really comes from a music background, does band posters, tours, concerts, and like festivals. And I feel like he really brought that mood into this poster. Just this beautiful, like decaying red sun, and this decaying what might be the remains of an exoplanet orbiting it. We took a little bit of artistic liberty there, but our scientists were still happy with us staying scientifically correct. So in the middle, we have a gamma ray burst poster. We have these space travelers who are observing the two neutron stars colliding and creating this gamma ray burst. We took a little artistic liberty here as well. We're kind of pushing the envelope a little from what we've done in the past. And then we have dark matter. This one was specifically challenging because how do you portray something visually that we don't know much about and that we can't really image? So our artist here, Ross, who's from New Zealand, he's done a lot of really beautiful, like colorful posters in the past and comic books. And so he created this idea, this arachnophobic poster, kind of inserting that dark matter spider into the cosmic web with that familiar tree lines. And it's a little too close to home, a little mysterious, but still pretty scary. This is the first time that we've created these posters in Spanish as well. So you're seeing the English versions, but we have their equivalents in Spanish. And that was the first product in our group that we had created both simultaneously English and Spanish products for. So our distribution strategy and our promotions through NASA reflected that. The way that we marketed these, we marketed them to English speaking outlets, Spanish speaking outlets. I know BBC Mundo picked it up, some outlets in Spain picked it up. So this was a great way for us to expand our reach to different audiences that might not necessarily be folks that we normally reach through our NASA products. From now on, we are going to be creating our products in English and Spanish as well, because the reception was just fantastic, and we're reaching historically excluded audiences from our products. So it's been great expanding this series and reaching more people through it, which is literally our jobs, to reach as many people as we can with NASA science. So this was specifically just really awesome. I'm really glad I was able to work on this series last year. We have some more coming up as well. Yeah.
Can I add to that quickly? So you might be looking at these posters and think, okay, why posters? And so one, this gets NASA and it gets these missions and it gets the science in front of people daily. It depends on where they hang these posters. It could be an office, it could be their home. People are hanging up in both of them. But now NASA is in front of a person on a daily basis, and whoever comes over to their desk. So you've entered the conversation of every day, which is good. Two, people don't know what gamma rays are. And now you've just pulled them into learning, right? Kind of your average group of people. These posters pull people into learning more about what the science is that's happening here. Some of the posters were like, well, why are these planets have really long, weird titles and names? There was sort of this uproar to like, name the planet something cool. Why do they have these numbers? Well, we've had such a great response too of people learning about why they have these really long names with numbers where uppercase and lowercase letters matter, So these things are tools to pull people into learning, and they're done in beautiful ways to keep that in front of people for the longest amount of time on a daily basis.
right? And we've seen these appear in pop culture shows. I know that some of the travel posters appeared in Queer Eye in the past seasons. These movie posters specifically, these posters are supposed to mimic horror movie posters in a vintage style. And the fact that they're movie posters alone allowed us to put a little more text to explain what you're seeing. So we're not tricking people into learning so much. We're just kind of, like Joby said, pulling them into learning more about these phenomena that you don't really hear about in everyday conversation. And like I said, the reception was fantastic. We ran these on NASA's Spanish channels as well, our social media. We partnered with different Spanish-speaking social media accounts too. This made the front page of Reddit. CNN ran it on their front page under Space and Science in time for Halloween. And these are all free, so you can download these in English or in Spanish to get them printed. Like Joby said, hang them on your wall. They are paid for by American taxpayers. They are available to anyone who can access our site, anyone who has internet and can download them and have them as their own. Thalia.
All right.
Go.
Did I miss the slide?
It's okay. I think
okay.
We're pressed on time, but so we actually began a new series of posters, and this is focusing on the telescopes and the amazing technology that we use to find these planets, to observe these amazing phenomena. And we actually just produced a test poster. It is being released this week. You guys are getting a sneak peek, and it will be available for download for the attendees of this conference. So as you can see, this is just showing you some of the rough drafts that we went through and the final product right there on the right-hand side. This is meant to highlight the technology in the spacecrafts that we use to find planets. This series is very specific to exoplanets, but we also like to highlight some of the other science that these telescopes do. And so in the background, you can see some other, stars and galaxies hidden in there. But yeah, this is available for download now. I think the file should be available for download somewhere on the MIT site, if I'm correct. And it is free for everyone to download and print out and hang up at home. We can go to the next slide.
Sorry guys, my slides are so jumpy today. There we go.
All right, and so this is the slide if you guys want to reach out to us. If you have any amazing science results that you would like to get visuals for, it is a NASA funded paper. Feel free to reach out to us. We would be happy to work with you. We're always looking for great new ideas. We're looking for different people to work with, and we'd be happy to help. Thank you. So if you would like to download all of the posters that we talked about today, you can visit our website, exoplanets.nasa.gov. We also have Twitter and Facebook for exoplanets, but also for any general astrophysics content. And I think we will be taking questions now.
Wonderful. Well, thank you all so much for that presentation and for kind of walking us through the creative process that goes into these products. I'm sure there's a lot of applause happening at everyone's respective living rooms. I'm sorry you can't hear it. You're just stuck with me instead, but I'll tell you, it was a great talk. For folks who are in attendance, if you have questions that you would like to ask our speakers, please drop those into the Exoplanets channel on Slack, and I'll keep an eye on that. And while we wait to see if there are some audience questions, I will take the moderator's prerogative and ask, when you have a new project, some team has come to you and said, I have this amazing science result. Kaitlyn and Leah, how do you decide which artists to reach out to, or what style you think is well suited to that science topic?
That is a great question. So it really depends on what the product is, more specifically what it's going to be used for. If it is accompanying material for like a press release, or if it is material of a new discovery, say we want to do a new planet, we want to do a poster for a new planet, then we'll get together, we'll brainstorm what this is going to look like, what the release is going to look like. We also have to figure out like whether it's worthy of a poster, if that makes sense. So we really try to get people with very big events. So we made a TRAPPIST-1 poster in time for the discovery of the TRAPPIST-1 system, or when it was announced to the public. But we also create products like visualizations, animations to accompany press releases. So I think our first step would be to figure out like what type of product this is, if it's a video, if it is a poster, if it is an animation. We do a lot of animations and visuals in-house, but sometimes if it's something that maybe we just, you know, if it's something that is, you know, we have a short timeline to work with, then we'll probably be like, okay, maybe we'll contract an outside artist who would be able to work on this. And we have an internal process for how we figure out who we work with. But it really just does depend on what the product is and what the use case is for it.
Yeah, and specifically for the astrophysics galaxy horrors posters, the dead galaxy, dark matter, and gamma ray. Joby historically did those posters. I remember last summer he was pretty busy though, so I didn't catch him in time. So we looked at artists, like Thalia said, externally who we could work with. We went through an external agency that represents very talented artists who do more commercial work. And we found the right people through their styles, looking at their portfolios, seeing if they fit. It was a very intensive process that Joby and I went through, kind of looking at all of these different artists. Joby was able to stay on as the art director, kind of guiding them through their artistic process with those 3 posters. So yeah, it's a lot of research too if you're going external.
And if I can just quickly add to what that research is that Kaitlyn's bringing up, we do look at what, you know, early on it was an era specific style of poster so we tended to look for artists that could do very simple screen printing type that specialized in sort of that art form of 1950s or era. So we looked at that artist, and then we looked at, you know, what other work were they doing? Did they have any appreciation for any kind of, you know, would they be into something like this, or would it just be a job? And we look at, you know, how they kind of carry themselves as an artist publicly, because we would be talking about them. You know, this artist did work on this, you know, in interviews or whatever, and they'll be talking about that they did work. So we do look at a few of those factors, and then kind of narrow it down to a few. And 100% of the time, the artist was just ecstatic to work, and it was like a dream come true for them, which was fun for us to connect some of these artists to a dream of theirs since they were kids, to work and do something in relation to, connected to NASA. But as Kaitlyn kind of came into this next phase of the poster and into another phase that she's working on right now, we've expanded in our artists that we look at to kind of no longer do that era specific, but just people who are really good and really passionate. And I think that last Galaxy of Horrors posters that we showed were people that, you know, one of them does work for Lonely Planet. The other one, as Kaitlyn said, is huge with hobbyists and people that collect movie posters. And so he's very big in that realm. And so that actually is a bonus for us, because that's added promotion for not only your mission, but the poster itself. When some of these artists have 50 to 500,000 followers, so on social media, you better believe they're talking about it. And that is free promotion that, you know, that is priceless, that we can't pay for. So we do look at all of those things. And as of late, we've really been looking at, okay, we've used some of these great artists in schools, but how can we shake it up? How can we be diverse? You know, let's get different people, different nationalities, different art backgrounds to really step in. And that's something that we're looking at now, is really kind of trying to find some unique artists with some unique backgrounds to really step in.
Yeah, I think representation is very important in this production process. And that's something that we do pay attention to, especially as we branch out and create more products that reach different audiences that speak different languages or have different abilities. So it's something that we're very sensitive to as well.
Excellent, because that's a focal point. We've got a question from Brett Skinner. It says, great talk. Question for Joby, though I think you, Kaitlyn and Thalia probably have thoughts on this too. All throughout your presentation, you spoke about the power of art in connecting science and the public. We even call these artists like yourself to be communicators. But do you have to be an artistic type in order to be a communicator, as you called it?
Yeah, absolutely not. You know, I work within an organization called 18X, and that's all of our media folks. So we have incredibly talented writers that help us with what should the poster say on the back, right? How do you include all of this in a very captivating way? And so we have people that just focus on that, just writing. We have news folks that just work on communicating it in news story form. We have web developers, we have AR, VR folks as well. That we have something called Eyes on the Solar System and Eyes on Exoplanets that was created by our AR, VR folks. We have photographers, we have archivists, we have all of these different people that their whole main job is to take the complexities of what all of you do, because I'm not studying what you study, but I'm fascinated by it. And we found out that so many other people are fascinated by it too, they just don't understand it. So yeah, you don't have to have an art degree or be an artist to effectively communicate these things. We have so many other people, writers, photographers, documentarians, people that just sit in a room with a camera and film you talking. And then that becomes a documentary later. But I will say it would benefit all of you in your communication if you learned how to sketch. So there's a lot of YouTube University things out there. There's a lot of books. No shame in getting drawing for kids books. I got a coding for kids books just so I can understand what's going on with that. So I would highly recommend for you as a tool in your tool belt to learn how to sketch and learn how to at least get some of your ideas down to show people. That'll just benefit you in the long run.
And I'll also add that, you know, a majority of the scientists and engineers I've worked with on these posters and these different products so far are already really great at communicating. Jen herself is helping with the new Galaxy of Horrors posters. We're doing an Exoplanet one, TBD, keep an eye out for Halloween. But I specifically asked Jen to be involved with the project because she's very good at boiling down concepts and making me, who's the equivalent of a 5-year-old in a PhD class when you're all talking about your science, to make these things more understandable. So, you know, you don't necessarily even have to be a creative or do that professionally to be a good communicator. It's a matter of boiling down the science to something that your audience can understand and really knowing your audience.
Kaitlyn
Good
takes
question.
my bullet points and makes them beautiful. On a related topic, so Andrew Jolly says that was fascinating. Thanks. A quick question. I'm sure you get to see lots of plots in scientific publications. What advice would you give to scientists to modify the presentation of their publication-ready plots when they might want to present results to a public audience?
If I could, Thalia, I saw you're going to react, but if I could speak into that, you know, I've seen your plots. I've seen your plots. They're fascinating to me. I think they're fascinating to me. I don't understand them, but my mind immediately goes to hierarchy. I want to know where I need to measure something and know, so I want to understand. But I think your most powerful tool is if you can create analogy to what, and I know we're talking about your plots. If there is some way to work in an analogy with everything that you're doing, even visually, that really helps a lot, because that's usually what happens in our meetings. I will have to ask a scientist, can you give me another example? You know, and then they'll go, oh, all right, it's like, I don't know, it's like this. And then they throw out this story or an analogy or a visual or another science element that exists on Earth, right? Well, it's like Antarctica in this part of the region. If you can connect what you're doing to an analogy, that will you'll jump light years ahead to communicating. In terms of visually, yeah, I always just say be careful of your colors. Of course, red means bad, green means good to people. There are just certain. I would maybe look at, it's a good online search, a good Google search. There are books about it. But if you can understand color, just how people naturally connect with color, that can help you in your hierarchy of your data. Also, last thing before I want to jump over to Thalia, there's the thought that you need to put everything down at one time. And I think that's where people get confused. You see it all great at one time on one thing, but there is nothing wrong with breaking your graph down into a story form in terms of one thing at a time. Let people understand this one thing, then add on to that, then on to that. And that helping people understand things in a slower context. So get away from that it's all got to be one slide. There's nothing wrong with breaking things down layer by layer on 10 slides, and then you go through it very quickly for understanding's sake. So that's my advice. I thought Thalia maybe wanted to say something as well.
I was just laughing because I've been in the room when I'm asking a scientist, like, what does this look like? Or like, can you explain like, you know, these plots? And I will be honest, it's very confusing to me. Sometimes I zone out, right? You know, and that's not very different from the response you might get from the general public, right? Like a lot of people aren't familiar with the work that you're doing or with the science. They may not even know what an exoplanet is or what you're talking about or what you're trying to depict. So I think simple is always better. Like Joby said, if you can break it down into different segments and, you know, maybe not explain it all at once in one plot, I think that's probably best. But also if you're trying to explain something, you know, to do with numbers or the amount of things, you know, visualizations are also really great. That breaks it down into, I think, something a bit more simpler, but more clean. You know, on our website, we have some resources of visualizations that you can take a look at if that's something that you're interested in. And then always, if you're in doubt, ask a communications expert or ask someone who is absolutely unrelated in your field if this makes sense. And if they say no, accept that it doesn't make sense and don't try to explain it to them for 10 minutes. Just try to either use an analogy or change your presentation of it. So it's definitely not a bad thing to want to communicate what you're, you know, the science that you're doing. But sometimes, I mean, people don't really understand the thing that you've spent years and years studying and, you know, doing research in. So definitely simple is always better. I also recommend looking at like different colors that you use, you know, making sure things are legible. If you're using specific terms that only you would know or people in your field would know, consider maybe changing those words out. And it also really depends who your audience is. If you're speaking to a group of graduate students, you know, you might have the perfect content, but if you're speaking to people who are in the general public or 10-year-olds, you might really consider paring down what you have in there.
I feel like that, please don't spend 10 minutes trying to explain the plot came from personal experience based on the grimace. Okay, a question from Natalie Vitalia. She says, wondering about funding mechanisms for art and science. There was a bullet on one slide that said proposed to NASA. Is there a funding program specifically for this type of work, or are these unsolicited proposals? We have a design lab at UC Santa Cruz that would love to support the sciences and help us to communicate complexity and wonder. Any advice for growing such a program based on the JPL experience?
Yeah, I would I'll briefly say that majority of, so when I first started about 10 years ago, there was a lot of just people unsure of the power of the arts. And I got to say that we weren't sure either. And so it was people, it relied on people coming to our little studio with money in their project that they just knew they wanted to do something different. They didn't want to kind of do a basic new, you know, kind of the typical route. We want to do something different. And so gradually over time, we've noticed that more and more projects are allotting a certain amount of money to make room for communication specifically for using art. And so that's kind of all I'll comment on. I understand there may be hurdles to getting money to specifically focus on art, and in which case, feel free to look at how art has helped a lot with these exoplanets, the things that we've talked about today. Take that as your case in point. But I think that trepidation to spend money on it is just people being unaware of its power, or maybe fear that someone on the outside might think that it's a waste to go towards somebody throwing paint in a corner somewhere, you know, to music. So hopefully today is different, that people can understand the power of art and communication. But in my experiences, the doors have been opening a little bit more and more as people have seen the power of it. They've been making room for it. So Thalia, Kaitlyn, any thoughts on that?
Yeah, so I mean, I would agree with that. You know, I think the more press that these products get, right, the more excitement, the more engagement we get, that's just, you know, further justification for why we continue doing this. Right now, we typically do take unsolicited requests to do specific pieces of art. We work very closely with missions and people working on NASA missions to produce content that they would benefit from in telling their stories. So right now it is very unsolicited. I am unaware of any specific funding for working with external groups at the moment. That's not to say that's something that's impossible to do, but as of now, I haven't heard of anything, but we do really want to expand the work that we do and open it up to other artists, right? People who maybe don't have the opportunity to work with NASA now, but would like to contribute somehow. So we always try to keep an open mind in making them feel included in the work that we do, but also giving them opportunities to also be communicators for NASA.
And I'll also add that we did mention that we do occasionally subcontract work out when we don't have the capacity to do it internally or when it makes sense to subcontract it out. So that's always a possibility too. We do have limited funding on our specific teams. There are many different outreach teams at NASA that kind of cover different themes like solar system and or science, specifically within astrophysics and exoplanet outreach. Me and Thalia, we do occasionally subcontract work out too.
Excellent. Galen Bergston says, art crew, how do you approach visual accessibility features like alt text? And do you have any projects that don't rely solely on visuals, i.e. data to audio conversions?
I'm so glad you asked this question. Sorry, guys, I'm very into this. So we are working on some initial kind of preliminary research into getting data sonification projects underway. But we do provide alt text for pretty much all of the visual resources on our site. So we have an in-house, Thalia and I work with an in-team web designer and web dev, and she's fantastic, and this is something that she's very passionate about as well. So our website is as accessible as we can make it beyond kind of the basic requirements. But we, absolutely with alt text, we want to get more into tactile displays. We're talking more about 3D printing. So we're hoping, ideally, we want our products to be as usable to people of as many, limited abilities as possible. If you can't see, you could hear it, or tactile displays as well. So we're trying in this arena. There's a lot of development to happen, but we're working with folks. I think there's someone located at Harvard that we'll be working with soon on getting some of these products underway. And Thalia, I don't know, sorry if I cut you off.
No, that's okay. I was going to say that we do currently work with a lot of other organizations that do heavily focus on this. So the partner that Kaitlyn was mentioning works at Harvard CFA, and they do a lot of work on tactile resources. And, again, trying to sonify, some of the data that we have. I think that there is a lot underway for trying to make improvements in that area. Of course, we're not the best at it, but we are heavily focused in that area and trying to make as much of the science that we work on and communicate accessible to as many people as possible. So that is always a goal for us, but also, we are open to listening to other people's idea. And I think that's the beauty of, giving people the opportunity to weigh in on the way that we communicate the science is, taking those ideas. If you have ideas for how to communicate these things in non-traditional ways, we would always love to hear them and, potentially work on them.
And we do realize that the gift that we can give to people, the greatest gift is that data that you all study, and how to have people, especially the artists, are hungry to co-create with that data. And so, as Kaitlyn was bringing up, the work of sonifying this. Now, there are a lot of tools that are able to do these things, but this is where I'm the jerk as the art, like a visual strategist. I come in. They're like, look at this great tool that sonified this data. And I'm like, yeah, but that sounds like garbage. That's like, someone's going to listen to that once. Your average person's going to listen to that once, and that's it. And they may not even find it fascinating. And so we're trying to figure out the development of tools that allows the data to be what it is, but allows people to create with it something beautiful for the widest amount of audience to be fascinated by it. So yeah, that's kind of our next step. But I would say that's the new frontier in gaining trust with our organization and different people in terms of, would you like to spend the time and the money on developing something like this? So it's sort of like you got to prove it a little bit, and then you get more trust, and you prove it a little bit, and you get more trust, and then you don't. So that's where we're at right now. But yeah, that's our goal, is to go into those areas.
Exciting. That's a fun expansion to be thinking about. Okay, let's get ready to wrap this up. Let's do one last question that is hopefully an easy one. David Wilson says, for all three of you, what's your favorite poster that you've worked on or made? Joby, maybe you have too many for this to be an easy question.
That's why I said I'm going to go last to filter through. So
I'll let Kaitlyn go first.
Yeah, I think one that I've produced, oh gosh, I think that gamma ray burst poster. I think that Shan was the name of the artist that Joby and I worked with on it, and I think he blew it out of the park. I think they all did. But his use of color and brightness and visual energy that you can really feel in that poster, I think perfectly, conveyed the point that we were trying to get across with the gamma ray burst poster. And I will throw it over to Thalia and say that I love the Spitzer poster that she recently came out with. The TESS one's gorgeous as well. But I've personally worked on Spitzer end of mission, and that telescope has a very special place in my heart. And I think that she just did it absolute gorgeous justice with the poster that she recently released. That was last week, I think, right? Maybe the week before.
2 weeks ago.
Yeah, it was on one of our slides, and it's Spitzer centered gorgeously in front of the TRAPPIST system with all of these bright, beautiful colors, and I absolutely love that one.
Thank you. That was a fun one to work on. If I had to pick a favorite poster, I'm going to pick two. So I'm not going to pick a favorite, I'm going to pick two. But one of my favorite posters to work on, just because it was so exciting to visualize it and figure out what this might look like, was one of the first posters in the Galaxy of Horror series. And that one is around a pulsar planet. So it's like PSR B1257, like plus 12C or something. So that system, it was really fun to visualize what that might look like. And working with scientists to just create something really beautiful was a really great experience. But I think one of my favorite posters so far that I've also worked on, just visually so stunning, is a poster that is actually not yet released. So unfortunately, I can't share any visuals with you, but it's the last poster that will be released in the Telescope series. And that poster is honoring the Webb telescope. And it's beautiful. I think the telescope is beautiful. The visuals are beautiful. So I'm really excited to get that released soon-ish so that you guys can see it.
And too many for me to point out. It's like, which one of your kids is your favorite? Which, be honest, you know which one is your favorite. That's always, all of you would probably say that. So no, I would say that my favorite posters are the ones where they just sort of write themselves. The idea is very clear. I think Thalia referenced the zombie posters, it's zombie worlds. There are just some posters that write themselves, like zombie worlds are cool. Even the names of the planets had crazy names that fed into that story. And then it was just very clear from the beginning, we're going to make a skull out of galaxies and stars. And so I love the posters that just sort of write themselves. And then that gives me a lot of freedom to play visually. The lava world ones are beautiful. It's a fun story, but they're exhausting. Where you're done, you think you're done, and then NASA says you're going to kill people. And you're like, oh my gosh, you're right. I don't know, here's a protective bubble, and then it just becomes about getting it as good as possible and out and making sense and hoping people doesn't blow. That's the scariest part, is putting something out there and hoping the world accepts it and loves it and does it. Am I missing am I missing like an innuendo in there? Am I missing something? Is the public going to see one thing and then not let that go? And that's always my fear. So I love the posters that are easy to do, go out, people love them, embrace them, hang them up, and then yeah. So thank you for letting us hang out today. It was a good, full, fun hour with
Yeah,
me.
thank you all so much for making the time for this. I'm sure there are a lot of positive comments in the Slack channel. People are big fans. It's fantastic and interesting to hear about what goes into making these posters that we all, love so much and hang up on literally any surface we can find. So we very much appreciate you coming and sharing your experience and your expertise. And it's been a great pleasure having you guys on.
Thank you. You're a
so
great
much.
moderator.
Thank you. Stay tuned for more to come.
Yeah, especially that James Webb poster. I'm excited now.
Great.
All right,
Okay,
everyone.
with that, we will wrap up this session. To our attendees, tune in tomorrow morning for day 3 of TESS-Con 2, and we will see you then.
Beautiful. Take care.
Thanks
everyone.
so much. Bye, everyone.
Good night.